Hello, great friends. I hope you are doing great. And I want to let you know that IBM is here with another episode of Learning Physics. And today, I think this will be part 3 of solved past paper questions of the unit we are actually talking about, which is force, density, and pressure. Do not forget this is AS Physics 9702. And these are solved past paper questions. Specifically, this is going to be part 3 of force, density, and pressure. Without wasting time, I would like to take you to the past paper document so that we continue from where we stopped in part 2. So in part 2, I think we stopped around here, and I want us to start from this same point. So a spring balance is used to weigh a cylinder that is immersed in a fluid in oil as shown here. So before we go even to the equations, we can try to think about the forces which are acting. If it is immersed in the oil, there could be an upthrust force, which I'm going to call U. Of course, it has a mass. There is a weight which is vertically downwards. Because the weight is vertically downwards, there must be tension in the wire, which I will call T, that will be vertically upwards. Those are the forces acting. Let's now see the questions. The reading on the spring balance is 4.8 newtons. The reading on the spring balance is 4.8 newtons. The length of the cylinder is 5 centimeters and the cross-sectional area is 13 centimeters per second. The weight of the cylinder is 5.3 newtons. The cylinder is in equilibrium when it is immersed in the oil. Explain in terms of forces acting. Explain this in terms of forces acting. It is in equilibrium. Remember, the tension is acting upwards and the upthrust is also upwards. If it is in equilibrium, then the tension upwards plus the upthrust upwards should be balancing with the weight. So the question is telling us to explain this equilibrium in terms of forces. So we shall simply say, let me try to reduce the weight. We shall simply say that for equilibrium, the resultant force is 0. The resultant force equals to 0 for equilibrium, and therefore the weight, which is the weight which is downwards, should be equal to the tension in the wire plus the upthrust, or the weight minus the upthrust must be equal to the tension. So for equilibrium, the resultant force is 0. That is, the weight downwards must be equal to the upthrust plus the tension in the wire, or plus the force from the wire. Force from the wire plus the force from the wire, which I'm calling the tension. So if there is equilibrium, the tension plus upthrust upwards should be equal to the weight downwards. Because for equilibrium, the resultant force must be equal to 0. Then calculate the density of the oil. Since they have given us the reading on the spring balance as 4.8, yet we see the weight of the cylinder is 5.3 and the weight is measured in air. So it means this is the weight in air, but this is going to be how it weighs when it is immersed in the oil. That means the difference in these two values of weight is the upthrust. So first of all, upthrust is going to be the difference in weight. Upthrust is going to be equal to the difference in weight. The difference in the weight. And this is going to be 5.3 minus 4.8. That is going to be the upthrust. And I think this is, I think that is 0.5. 5.3 minus 0.8, I mean 4.8. That is 0.5, which is a half. So the up thrust is 0.5. But remember, up thrust is cross-sectional area times difference in pressure. So up thrust is equal to the cross-sectional area times the difference in the pressure. And that means 0.5 is going to be the cross-sectional area, and the difference in pressure will depend on the density times G times the difference in height. That is the difference in pressure. So we are substituting. This will be 0.5 equals to the cross-sectional area. They gave us 13 centimeters squared. We change it to meters squared. So it will be 13 times 10 power negative 4 meters squared. The density is what we want to find. G is 9.81. Then the difference in height is just going to be the height of the cylinder or the length of the cylinder, which is going to be equal to 5 times 10 power negative 2 to change it to meters. So I'll just press my calculator and I will say 13 exponent negative 4 times 9.81 times 5 exponent negative 2. So I will say 0.5 divided by the answer. So the density is 784. So density is equal to 784.1 or approximately 780. So that is the density. 780, 784. That is the density. Okay, the cylinder is made from a material of density 2.7 grams per centimeters cubed. The cylinder has diameter 2.4 centimeters and length 5.0 centimeters. Show that the cylinder has weight 0.6 newtons. So density, we know density is mass over volume first of all, and we know that the volume is going to be pi r squared times another length or h. Because it's a cylinder, you can think of the height h. But since we have been given the diameter, the radius is diameter over 2. So this is going to be pi. Where there is radius, I'll put d over 2, but this is squared, then times L. So this is pi d squared over 4 times L. That is the volume. Remember, I want the weight, which weight is going to be mass times G. So the mass is density times volume. So the mass is going to be the density times the volume, which is pi d squared L over 4. That is the mass. And to find the weight, I know that weight is going to be m times g. So it means this is going to be density times pi times d squared over d squared L over 4. Then I multiply this by g. So I will substitute this just for once and for all. So the weight is going to be density. The weight is in newtons, so the density should also be in SI units. The density in grams, I multiply it by 1,000, it becomes 2,700 kilograms per meters cubed. The diameter is going to be, by the way, we would have used the radius, there's no problem with that, but me, I prefer to use the diameter. So the density is 2,700. I'll first multiply by G, which is 9.81. I multiply this by L. L is 5 times 10 power negative 2 to change it to meters, times pi times D. The diameter is 2.4 times 10 power negative 2, but this should be squared. Then the whole of this can be divided by 4 because there is a 4 there. The order of multiplication doesn't matter as long as every quantity is added there. So I have 2,700 times 9.81 times 5 exponent negative 2. Okay, times pi times, I'll open the brackets, 2.4 exponent -2, and this is squared. Then I divide this by 4. So this is giving 0.599, 0.599, which is approximately 0.60 in newtons. So that is going to be the weight. You would have first found the volume, then after finding the volume, you find the mass. After finding the mass, you substitute in the equation for weight and find the weight. But I just wanted to substitute at once. The cylinder in A is hung from the end A of a non-uniform beam, a non-uniform bar AB as shown here. Okay. The bar has length 50 centimeters and has weight 0.25. They say the bar is non-uniform, so I can't put the weight at its midpoint. It is already put somewhere there. The center of gravity of the bar is 20 centimeters from end B. So we can predict that this distance here is actually 50 minus 20, which is 30 centimeters. The bar is pivoted at P. The pivot is 12 centimeters from B. We can also predict that this distance here is 20 minus 12, which is 8 centimeters. Explain what is meant by, okay, an object X is hung from end B. The weight of X is adjusted until the bar is horizontal and in equilibrium. Explain what is meant by center of gravity. We have seen this before in previous parts. Center of gravity is a point where all the weight of a body may be considered, all the weight of a body may be considered to act. That is center of gravity. Then calculate the weight of X. So we are going to take moments to find the weight of X. If we take moments about point P, you notice that X will cause that kind of moment, which is clockwise. The weight causes that anti-clockwise. The cylinder causes anti-clockwise. So taking moments about P. Taking moments about P. So the weight W times its perpendicular distance. The weight W times its perpendicular distance, which is from pivot, is 12. I may not convert the units because I know centimeter is going to cancel since I am equating moments. On the other side, for the anti-clockwise moments, we have 0.25. 0.25 times the perpendicular distance, which we have seen as 8 centimeters, plus the weight of the cylinder, which is 0.60, times the perpendicular distance from P, which is going to be 30. That is 30 plus 8, which is actually 38, or 50 minus 12, which is 38. So this is times 38. So we can simplify this. On the right hand side, I have 0.25 times 8 plus 0.6 times 38, which gives me that. Then I divide this by 12, and that is 31 over, that is 2.06 recurring. The 6 is recurring, so that is 2.07. So weight W is equal to 2.07, or we can just write this as 2.1. So this is going to be 2.1. That is 2.1. The cylinder is now immersed in water, as illustrated in the figure below. An upthrust acts on the cylinder and the bar is not in equilibrium. Of course, when the cylinder is immersed in the water, there is an upthrust on the cylinder, so the bar is not in equilibrium. In other words, the anticlockwise moments have been reduced. Explain the origin of upthrust. We know that upthrust is as a result of the difference in the pressure on top of the object and at the bottom of the object. So since we are referring to a cylinder, so we shall say that since pressure changes with the depth, since pressure changes with the depth, since pressure changes with the depth, the pressure on the bottom of the cylinder is actually greater. Pressure on the bottom of the cylinder is greater than pressure on top of the cylinder. Pressure on the bottom of the cylinder is greater than pressure on the top of the cylinder. So it means the force up on the bottom of the cylinder is greater than the force down on the top of the cylinder. The force up on the bottom of the cylinder is greater than the force down on the top of the cylinder. So that difference in pressure causes a force. There is a force here due to the pressure at the bottom. There is a force on top due to the pressure at the top. But remember, force is equal to pressure times area. So since the pressure at the bottom is greater than the pressure at the top, it means the force at the bottom, which is upwards, is greater than the force at the top, which is downwards. That is the origin of upthrust. Explain why the weight x must be reduced in order to obtain equilibrium for AB. So since we have seen that the force at the bottom is greater than the force at the top, it means the anticlockwise moment has actually been reduced by immersing the cylinder into the water. So it means we must move x in order to restore equilibrium. So the question is, explain why the weight of x must be reduced in order to obtain equilibrium for AB. So we have seen that immersing the cylinder into the water has reduced the anticlockwise moment. Or we are seeing that the clockwise moment caused by x is now greater than the anticlockwise moment. If we don't reduce x, then it means equilibrium cannot be restored. So we shall say, immersing the cylinder reduced anticlockwise moment reduce the anti-clockwise moment. So it means the clockwise moment must be reduced. So clockwise moment must be reduced. Clockwise moment must be reduced since it's now greater. So there is no any other way we shall reduce the clockwise moment because we can't move x any further from the pivot since it's already at the extreme end. So all we need is to reduce the size of x. So I said since it's now greater, and this can be achieved by reducing the weight of x. And this can be achieved by reducing weight x, by reducing the weight of x. So that is how we can restore equilibrium. We have to reduce x so that we make the clockwise moment to be relatively smaller, or to be reduced so that it balances with the anti-clockwise moment, because immersing the cylinder into the water reduced the force this side, the force downwards. That means the upthrust, of course, the upthrust force reduced the weight of the cylinder, which meant that the sum of the total clockwise or anti-clockwise moment is now less than the clockwise moment. Okay, so we have to reduce the weight so that the clockwise moment can now balance with the anti-clockwise moment. A solid cylinder is lifted out of oil by a wire attached to a motor. The figure shows two different positions, X and Y, on the cylinder during the lifting process. Of course, before we go to the questions, we can identify the forces acting. When it is immersed in the oil, there is weight downwards. Of course, there is an upthrust force upwards. There is tension in the cable or in the wire. Of course, when it is just on the surface, there is only weight downwards and there is tension upwards. Unless it is actually submerged. Okay. The motor is fixed to an overhead beam. The cylinder has cross-sectional area 0.018 meters squared, length 1.2 meters, and weight 560 newtons. The density of the oil is 940 kilograms per meters cubed. Throughout the lifting process, the cylinder moves vertically upwards with a constant velocity. Which is 0.02 meters per second. The viscous force of the oil acting on the cylinder is negligible. That means the resistance force is negligible. Calculate the density of the cylinder. So let's begin with the density. Density is equal to mass divided by volume. And the mass, they gave us the weight of the cylinder. So the mass is going to be equal to the weight divided by G, which is going to be 560 divided by G, which is 9.81. So this is going to be 560 divided by 9.81, that is the mass. Then we divide this by the volume. Volume is equal to cross-sectional area. Volume is cross-sectional area times another length or another height. So the cross-sectional area was given as 0.018 and the length of the cylinder is 1.2. So this is going to be 0.018, that is cross-sectional area times 1.2. That is going to give us the density. So density is going to be 560 divided by 9.81. Then we divide this by 0.018 times 1.2. So that is our density, 2642.8. So So this is 2642.8 kilograms per meters cubed, which is the same as 2600 kilograms per meters cubed. For the cylinder at position X, show that the upthrust due to the oil is 200 newtons. For the cylinder at position X, show that the upthrust due to the oil is 200 newtons. So what is upthrust? Upthrust is due to the difference in pressure. So upthrust is equal to the cross-sectional area times the difference in pressure. And we know that the difference in pressure is equal to the density times G times the difference in height H. So we just substitute. Upthrust is going to be cross-sectional area was 0.018. Then density, we are substituting for change in pressure. Density of the oil is 940 times G, which is 9.81. Then the difference in height is just going to be the length of the cylinder, which is 1.2. That is going to give us the upthrust, 0.018 times 940 times 9.81 times 1.2. So that is 199.18. 199.18, which is approximately 200 as required. Then calculate for the moving cylinder at position X the tension in the wire. Remember, it moves with a constant speed, a constant velocity. That means the resultant force is always zero. Remember, we are looking at it at position X. So since it moves with a constant speed, so it's constant velocity, it has constant velocity, resultant force is equal to zero. F resultant is zero. So the forces we have drawn here on the diagram are the tension upwards, upthrust upwards, and the weight downwards. So since it is in equilibrium, the tension plus upthrust should be equal to the weight. Therefore, we shall simply say that the tension upwards plus the upthrust should be equal to the weight. So the tension is equal to the weight, which is 560, minus the upthrust, which is 200. 560 minus 200, that is 360. So the tension is 360 newtons. Then the power output of the motor, we know now that power is force times velocity. Power is force times velocity. The force, because we want the power output of the motor, this is going to be the force is going to be the tension in the cable or in the wire, because the tension in the wire is as a result of the power of the motor, since some of the force or some of the weight, the effect of the weight has been reduced by the upthrust. So this is going to be 360 times the value of the speed, which is 0.02. So we press our calculator, 360 times 0.02, and that is 7.2. So the power is 7.2. The cylinder is raised with a constant velocity from position X to position Y. State and explain the variation, if any, of the power output of the motor as the cylinder is raised. Numerical values are not required. Of course, as the cylinder is raised, the upthrust is reducing. The power is going to depend on the tension in the cable times the speed V. But remember, the tension is upwards and the weight is downwards. We subtract the upthrust, because tension plus upthrust was equal to the weight at constant speed. So we are seeing the upthrust reduces as the depth reduces. As we raise the cylinder upwards, the upthrust reduces because the upthrust depends on the pressure due to the liquid above that given point. The difference in the pressure is going to be the upthrust. So the upthrust is reducing. If the upthrust is reducing, the weight is not changing. It means this difference here is becoming larger. Because the upthrust is becoming smaller, the difference is becoming greater, meaning that the tension is becoming higher. As the tension becomes higher, it means that the power is going to be increasing. So we are saying, since upthrust decreases, since upthrust decreases, tension in the wire, tension in the wire increases. We have seen why it increases. If the upthrust decreases, the difference between weight minus upthrust becomes bigger. Therefore, the tension in the wire increases. And remember, the power is depending on this tension. So we say the power output of the motor increases. So the power output, of the motor increases. Okay, the rate of energy output of the motor is less than the rate of increase of gravitational potential energy of the cylinder. Without calculation, explain this difference. They are saying the rate of energy output, that is power output, is less than the rate of increase of gravitational potential energy, that is power required to increase gravitational potential energy. Without calculation, explain this difference. So if the rate of energy output of the motor is less than the rate of increase of gravitational potential energy of the cylinder, then there should be an explanation for this difference. Number one, as the cylinder rises, the gravitational potential energy of the oil decreases simply because when you look at the oil, as the cylinder rises, the level of the oil reduces. The level of the oil goes down because the oil goes to replace the position where the cylinder was. So since the gravitational potential energy of the oil decreases as it fills the space left by the cylinder, that means by conservation of energy, total energy is supposed to be constant, which means that the rate of energy output must be less than the rate of increase of gravitational potential energy because total energy must be conserved. Since the gravitational potential energy decreases, it means that the rate of energy output of the motor should also be less than this decrease. Oil will go to fill up the space where the cylinder was, so it means its vertical height reduces. So the gravitational potential energy is going to decrease. Alternatively, we can think about this in terms of work done on the cylinder by the upthrust. Some work is being done on the cylinder by the upward force. That's why the rate of energy output of the motor is less than the rate of increase of gravitational potential energy of the cylinder. So it means some work is being done on the cylinder by the upthrust. It's not only the motor doing work onto the cylinder. So we can say some work is done on the cylinder by the upthrust. Some work is done on the cylinder by the upthrust. Or we can say, we talk about gravitational potential energy. I'll simply say gravitational potential energy of the oil decreases as it falls as not as it falls, as it fills. Gravitational potential energy of the oil decreases as it fills the space left by the cylinder. And so total energy is conserved. And so total energy is conserved. State what is meant by work done. Of course, at this point, we now know work done. Work done is force times displacement in the direction of the force. Force times displacement in the direction of the force. A diver releases a solid sphere of radius 16 centimeters from the seabed. The sphere moves vertically upwards towards the surface of the sea. The weight of the sphere is 20 newtons. The upthrust acting on the sphere is 170 newtons. The upthrust remains constant as the sphere moves upwards. Calculate the density of the material of the sphere. So we now know that density is mass over volume. And since it is a sphere, we know the volume of a sphere as being 4/3 pi r cubed. They gave us the radius of the sphere as 16. So we just substitute here the mass. They gave us the weight of the sphere, so the mass is going to be the weight over g. So this is going to be 20 divided by 9.81. Then I divide this by the volume, which volume is 4/3 pi times the radius, which is 16 centimeters, that is 0.16, but is raised to power 3. So I just press my calculator, 20 divided by 9.81, then divide by how should I do this? Okay, divide by 4/3, divide by 4/3, pi times 0.0 means 0.16 cubed. So that is 118. That is 118.8, which is approximately 120 kilograms per meters cubed. Briefly explain the origin of upthrust. So we have noticed, since it is a sphere, pressure on the lower surface of the sphere may not be the same as pressure at the bottom surface. At the top surface. In fact, pressure at the lower surface is greater. So pressure on the lower surface of the sphere is greater than the pressure on the upper surface. So remember, force is equal to pressure times area. If pressure on the lower surface is greater than the pressure on the upper surface of the sphere, it means the force at the lower surface is greater than the force at the top surface. Therefore, the resultant force is upwards, giving it the name upthrust. Calculate the acceleration of the sphere as it is released from rest. So to find the acceleration, we need the resultant force. Acceleration is equal to the resultant force divided by the mass. So the resultant force we can check. The upthrust is 170 newtons. The weight downwards is 20. That means the upthrust is greater than the weight. The sphere is moving upwards. So the resultant force is 170 minus the upthrust divided by the mass. We saw that the mass was the weight over g, which is 9.81. So this is going to give us 170 minus 20 divided by 20 over 9.81. That is 73.5.6 or 74. So this will be 74. Then the viscous drag acting on the sphere is given by that expression, where r is the radius of the sphere and v is its speed. The constant k is equal to 810 kilograms per meters cubed. Determine the constant terminal speed reached by the sphere. The constant terminal speed. Of course, at constant speed means the resultant force is 0. So since the sphere was released and is moving upwards, of course the upthrust force is upwards, and the upthrust force is upwards. The weight is downwards, and since motion is upwards, then it means the drag force is downwards also. So the question is, determine the constant. The viscous drag acting on the sphere is given by that expression. The viscous drag is actually friction. The upthrust force is upwards, and the viscous drag is actually opposing the motion of this sphere. Let's try to look at this in a simple scenario. So the sphere is released from the bottom and the weight is vertically downwards, but the upthrust force is upwards, and the viscous drag because motion is upwards, I think the viscous drag is going to be downwards. So the viscous drag is downwards, D is downwards because motion is upwards. So the viscous drag at D plus the weight downwards should be equal to the upthrust if the speed is constant. So which means the drag at D is going to be the upthrust minus the weight. So this is going to be the upthrust, which is 170 minus the weight, which is 20. So the viscous drag is going to be 150. So we can now find the speed v. So d is going to be equal to k. I think they gave us k. D is k, r squared v squared. So d is 150. K is 810. R is the radius of the sphere, which I think they gave us as the radius is 16 centimeters. So this will be 0.16, and that is squared, then times v squared. So we just find v, 150 divided by open brackets 810 times 0.16 squared. which gives us that. Then we find the square root of the answer, which gives us that 2.689 or 2.7. So the speed is 2.7. V is 2.7. The diver releases a different sphere that moves with a constant speed of 6.3 meters per second, directed towards a stationary ship. The sphere emits sound of frequency 4850 Hz. The ship detects sound of frequency 4870 Hz as the sphere moves towards it. Determine to three significant figures the speed of sound in the water. To three significant figures. So the observed frequency F0 is equal to V minus US divided by Fs. Because the observed frequency is higher, the denominator will have a minus instead of a plus. So the observed frequency is 4870. This is equal to V divided by V minus 6.3. And this will be times the normal frequency, which is 4850. So it means I will divide by 10. So you have 487 divided by 485. The 0 has gone is equal to V over V minus 6.3. So you cross multiply and find your value of V the way you want. I will do this just for PCB students. So I have 487 times V minus 487 times 6.3 is equal to 485 times V. I collect like terms. I'll bring the one with V on the left hand side. 487 minus 485. I mean 485. That is 2. So I have 2V is equal to, the other side I have 487 times 6.3. That is 30681. 306.81. So I divide the answer by 2. And that is 1534. So this means V is 1534, which is approximately 1530 meters per second. Okay, distinguish between the mass of a body and its weight. So we know that mass is a measure of a body's resistance or inertia to change in motion or velocity. A measure of a body's inertia. Measure of a body's resistance, or you can call it inertia. A measure of a body's resistance or inertia to changes in motion. To changes in motion or velocity. Or you could say mass is a quantity of matter. Quantity of matter in a body. Quantity of matter in a body, quantity of matter in an object, that is mass. Then of course weight is the force of gravity on a mass. Force of gravity. Force of gravity on a mass, that is mass. Or you could go ahead and say, because they gave you 3 marks to give the difference, you could say mass is constant and weight varies. Mass is constant and weight varies. Or you would say mass is a scalar. Mass is a scalar. It is scalar. force of gravity on a mass, and it is a vector. So that will give you the third mark. You can't just distinguish without giving more details and get 3 marks, not at all. State 2 situations where a body of constant mass may experience a change in its apparent weight. Of course, we have said weight varies, even when the mass is constant. What makes weight to vary? Weight is normally equal to mg, and that means g can vary. When an object is immersed in a fluid, the upthrust makes the object to appear as if it is weightless or it has reduced in weight. So one, it could be change in the fluid surrounding the object, change in the fluid surrounding the object, change in the fluid surrounding the object. If you are weighing in air and then you weigh when the object is immersed in the liquid, you don't expect to get the same weight. Number two, where gravitational field strength changes, or where acceleration due to gravity changes. Where gravitational field strength changes. Where gravitational field strength changes, we expect the weight to also change. That is why we say the apparent weight will be different, because weight depends on gravitational field strength G. Where the gravitational field strength changes, the weight will also change. You can't have the same weight on Earth as it is on the moon. It is different. Then when you change the surrounding fluid, if you are weighing in air and then you weigh the object in liquid, you don't expect to get the same weight. Define the moment of a force. So we now know that moment of a force is the product of force times perpendicular distance. Force times perpendicular distance of the line of action. Of the line of action of the force from the pivot. Force times perpendicular distance of the line of action of the force from the pivot, that is moment. State the two conditions necessary for a body to be in equilibrium. We have said there should be no resultant force, or the resultant force should be zero. No resultant force in any direction. No resultant force in any direction. Number two, no resultant moment. No resultant moment about any point. Or the resultant moment about any point should be zero. Okay, those are the conditions. We have repeated them several times and you should now be familiar with them. For a body to be in equilibrium, the resultant force is zero and the resultant moment or resultant torque is zero. Two parallel strings, S1 and S2, are attached to a disc of diameter 12 centimeters, as shown here. So this distance between the two points of attachment is going to be 12 centimeters. And if the string is affixed the other side and this side, it means the tension here is in that direction and the tension there must be in that direction. So the question is, okay, the disc is free to rotate about an axis normal to its plane. The axis passes through the center C of the disc. A lever of length 30 centimeters is attached to the disc. When a force F is applied at right angles to the lever, So the force F is at 90 degrees to the lever. So this force is at 90 degrees to the lever, so it can cause a moment about the center because the perpendicular distance will be 30 centimeters from the center. When a force F is applied at right angles to the lever at its end, equal forces are produced in S1 and S2. The disc remains in equilibrium. On the figure, show the direction of the force in each string that acts on the disc. So the forces are in that direction. These are tensions, one in that direction, one in that direction. They are equal but opposite. Those constitute what we call a couple. Then the force, for a force F of magnitude 150 newtons, determine the moment of force F about the center of the disk. So we have already seen that moment is the product of the force and the perpendicular distance about that fixed point. So the moment is going to be 150 times the perpendicular distance, which is 30 centimeters. That is 30 over 100. To change it to meters. So that gives us 150 times 0.3. 150 times 0.3, that is 45. The torque of the couple produced by the forces in the strings. So we are going to determine the torque of the couple. Torque is the product of one of the forces and the perpendicular distance between the two forces. Because the moment caused by this force, let's see, the moment caused by this force is actually anti-clockwise. The torque caused by these ones is actually clockwise. So this one in S1 is in that direction, in S2 it is in that direction. So the torque caused by the tensions in the strings is clockwise. The torque or the moment caused by the force F is anti-clockwise, but the disk is in equilibrium, so it means the resultant moment is zero. Therefore, the moment due to the force F must be equal to the torque. So this is going to be 45. For equilibrium, the resultant moment is zero. For equilibrium, resultant moment is zero. So since the torque or the moment due to the couple is clockwise and the moment due to the force F is anti-clockwise, the resultant of these two should be zero. So the other one, the moment of the couple should also be 45 so that the resultant is zero. Then the force in S1. So we know that the torque is the product of one of the forces and the perpendicular distance between them. So torque is equal to one force times perpendicular distance. One force times perpendicular distance between them, and the torque is 45. So 45 is equal to one force, which I will call the tension in S1, times the perpendicular distance between the two forces, which was 12 centimeters, I guess. That is 0.12 in meters. So that will be times 0.12. So this gives us the torque as 45 divided by 0.12. 45 divided by 0.12, that is 375. State the relation between force and momentum. At this point, we know that force is the rate of change of momentum. Force is equal to the rate of change of momentum. Force is the rate of change of momentum. A rigged bar of mass 450 grams is held horizontally by two supports, A and B, as shown in the figure. So its mass is 450 grams. The support A is 45 centimeters from the center of gravity. So C is the center of gravity of the bar. and support B is 25 centimeters from C. A ball of mass 140 grams falls vertically onto the bar such that it hits the bar at a distance of 50 centimeters from point C. So the ball will hit a bar here and will exert a force which is going to be its mass times G. Let's say let me say M times G. The mass should be in kilograms. Here they gave us grams, that is 0.14 in kilograms. I think it is 0.14, that is 140 divided by 1000, 0.14. So this force it exerts is 0.14 times G, which is 9.81. Then its weight, its mass is 450 grams, the mass of the bar, and the mass acts at the center. So let's say that the weight here is 450 is 0.45. Then we multiply this by G. Okay, so there's a force here which is vertically upwards. This is the force due to the at point B normal reaction. And there's a force here which is going to be vertical downwards. I'll call this one force due to A. The variation with the time t of the velocity v of the ball before, during, and after the bar is shown in the figure. Okay, so they have showed us a graph of velocity against time before, during, and after. So that means this part here is before, and this part here which goes downwards, it is during. So during is between during is taking two small squares between this point and that point, that is during. And then after is the one which is showed parallel to the other one. Okay, let's see the questions. For the time that the ball is in contact, we have seen that in contact is taking two small squares between this point here, which is along this line, and then here, which is along this point here. So this is in contact. And the scale on the x-axis is 0.2 divided by 10, that is 0.02. There are two small squares, that means the time of contact is 0.02 times two small squares, that is 0.04 seconds. That is the time in contact. Okay, so determine the change in momentum of the ball. Let's begin with the change in momentum of the ball. For the time that the ball is in contact with the bar, use the figure to determine the change in momentum of the ball. So momentum is mass times velocity. We want the change in momentum, which will be the mass times V1 or V2 minus V1, change in velocity. So let's substitute. The mass was 140 grams, which is 140 times 10 power negative 3. On hitting, its initial velocity is, we can read the velocity here, it is in the middle of the box. It is somewhere here in the middle of the box. On the vertical, the scale is 2 divided by 10, which is 0.2. So each small box is 0.2. So this is 1, 2, 3, 4, 5. That is 5, 5.2, 5.4, 5.5. So this is 5.5. Then when it hits, the speed changes. It is now here. It is negative 4. So it changes from 5.5 to negative 4. That is the change in speed. So this is going to be, let's say 5.5 minus negative 4. Or you can say negative 4 minus 5.5. There is no problem. The magnitude is going to be the same. So this is going to be, let me say V1 minus V2. So this is going to be 140 exponent negative 3 times 5.5 plus 4, which is 1.33. So this is 1.33. That is the change in momentum. Then use the figure to show that the force exerted by the ball on the bar is 33. So by definition, force is equal to the rate of change of momentum. We have seen the change in momentum as 1.33, and the time of contact, we have already seen that the time of contact was 0.04 from the graph. We check, divide by 0.04, that is 33.25, which is approximately 33 newtons. For the time that the ball is in contact with the bar, use data from the figure 3.1 and B part 2 to calculate the force exerted on the bar by the support A. For the time that the ball is in contact, that means we shall use the force exerted by the ball on the bar, which is 33. Use data from the figure to calculate the force exerted on the bar by its support A. So we go back to the graph, to the diagram. So we have seen the force exerted by the ball on the bar is 33 newtons. So this one is going to be 33 newtons. But remember, it exerts this force at a perpendicular distance of 50 plus 25. And that one causes an anticlockwise moment. The weight of the bar causes anticlockwise moment. FB will have no moment because it's acting through the pivot B. And FA exerts a force downwards, is causing a clockwise moment. So taking moments about B, we shall say that FA times perpendicular distance, which is 45 minus 25, that is 20, should be equal to 0.45 times 9.81, that is the weight of the bar, of the beam of the bar. Its perpendicular distance is 25 plus the 33 newtons, that is the force exerted by the ball when it hits the bar, times its perpendicular distance, which is I think 75, that is 50 plus 25. So those are the moments that we are going to actually take. So taking moments about B. Taking moments about B, the ball exerts a force of 33 times perpendicular distance, we have seen is 75. That is an anticlockwise moment, plus the weight of the beam is 0.45 times G, which is times 9.81, that is the weight, times perpendicular distance, which is 25. This should be equal to the clockwise moment, which is FA, times perpendicular distance, which is 20. So we can solve this. 33 times 75. Note that I didn't change the units of the distance because I know the units are cancelling on both sides. They are the same units on both sides of the equation. So 33 times 75 plus 0.45 times 9.81 times 25. So that's what we have. I will divide this by 20 to make F the subject. That's 129.27, which is approximately 129 or 130. Then we want now to calculate the force exerted on the bar by support B. Let's go back to the diagram. So at that time, the force here is 33 newtons downwards. The force here is 0.545 times 9.81. The force on A, we have got it as 129. This should be the sum of forces downwards should be equal to the sum of forces upwards. And upwards we only have FB. So it means FB is going to be equal to the sum of the forces downwards. So we shall say FB is equal to 33 downwards plus 129 downwards plus 0.45 times 9.81, which is also downwards. So this gives us 33 plus 129 plus 0.45 times 9.81 downwards, and that gives us 166.4, or approximately 166 newtons. A block of wood of weight 25 newtons is held stationary on a slope by means of a string as shown in the figure. So that is what we have. We can first of all try to draw some lines here so that we resolve some of these things, because we already have ideas about resolving along a plane. So parallel to the plane, and we can find perpendicular to the plane. So perpendicular to the plane, you and me will see that this angle is 35 degrees. It is the same as that one. When I resolve 25 perpendicular to the plane, it will be 25 cos of 35. Parallel to the plane, it will be 25 sine of 35. So I can have two equations here. If this is in equilibrium, because they say it is held stationary, I have that R is the same as 25 cos 35. I also have along the plane, T is going to be equal to 25 sine of 35. So let's see the questions. Let's see the questions. The questions say that either by scale diagram, either by scale diagram, either by scale diagram, either by scale diagram on the figure or by calculation determine the tension T in the string. So I've seen that T, by resolving 25 vertically perpendicular to the plane and parallel to the plane, I see that T is equal to 25 sine 35 degrees, which is actually 14.34 or 14.33. I think that is the easiest. You can use a scale diagram. So method one, we are having that T is equal to 25 sine 35, which is 14.3. I've simply decided to resolve the weight. Now let me just ignore resolving the weight and I resolve R. If I resolve R, I can resolve R parallel to the plane. I can resolve R in the horizontal plane and in the vertical plane. That means I'll use a different color for resolving R so that there are two different methods. So since 25 is in the vertical, I'm going to resolve R in the vertical and in the horizontal. So I'm trying to draw a horizontal line here. When I resolve R in the horizontal, it will point in this direction and to be R sine 35. When I resolve R in the vertical, it will point upwards and to be R cos 35. So in that case, we notice that R cos 35 should be equal to 25. R cos 35 is going to be equal to 25. And when I resolve R in the horizontal, it is actually R sine. Oh, sorry, let me resolve it. If I resolve R in the horizontal, it is R sine 35. in the horizontal. If I resolve it parallel to the plane, it will be r sine 25. That means r sine 35 could be equal to the tension T. So it means I can combine these two equations. And I say that r sine 35 divided by r cos 35 is equal to the tension over 25, which means that the tension T is equal to 25 tan of 35, which I think is the same as 25 tan 35. Is it 25? No, I think I resolved wrongly. Let me check it again. So I resolve, no, this is r sine 35 in the horizontal. It means I will also have to find a t in the vertical. This maybe let me leave this method because it is going to involve a lot of resolving here. It is going to involve too much resolving here and there. But r cos 35, r is equal to 25 cos 35. I think that is easy. And then t upwards is equal to 25 sine 25. I think that is easy. So it means I have, if I resolve r and t, I have to resolve r and t vertically and horizontally, which will be very long, but let me still persist and do it because I know. Okay, I'm going to resolve r and t both in the horizontal and in the vertical because they are not in the t has a component in the vertical as well as in the horizontal. It has a component in the r also has a component in the vertical as well as in the horizontal. So let us see. Resolving r in the horizontal, I got r sine 35. This angle here must be obtained. Let's see what that angle is. If this angle is 35, I've drawn a horizontal line here. So this angle here is going to be 55. This angle is 55. That angle is the same as this one. This is 55. And it means that this angle is going to be 35. So this angle is also 35. So I've resolved r in the horizontal. I'm going to resolve t in the horizontal. The horizontal is this one here. So this is going to be t cos 35. Then I'm going to resolve t in the vertical. Resolving t in the vertical, it will be t sine 35. So vertically, I have that r cos 35 plus t sine 35 should be equal to 25. That is in the vertical. Then in the horizontal, I have that r sine 35 and that is r sine 35. That is if I have not resolved. Remember, it means I have not resolved the 25. So I have r sine 35. Then in the horizontal, the other side, I will have t cos 35. Yes. If I resolve t and r without resolving 25, that's what will happen. So I substitute one into the other. So it means r is going to be equal to t cos 35 divided by sine 35. So I will go and substitute for r in that expression. So I have that t cos 35 over sine 35 times cos 35 plus t sine 35 should be equal to 25. So I'm just going to press the calculator to find t. So in the brackets I have cos 35 times cos 35 again, divide by sin 35, then plus sin 35. So I'll get 25 divided by the answer. So we are having cos of 35 times cos 35 again, divided by sin 35 plus sin 35. Then I have 25 on the right hand side, so I'll say 25 divided by the answer. I'm making t the subject, remember. So it means t is 14.33. So t equals to 14.33 newtons. This requires a very able student to resolve. Another student would draw a vector triangle and draw this to scale. How? Fix a vertical line which is of 25 newtons. Then on this vertical, you are going to measure off an angle of 35 degrees. This is going to be 35 degrees. So this will be R. Then now, you notice that the tension is making an angle of 55 degrees with the horizontal. So on the scale that you have chosen to represent 25 newtons, where 25 stops, you can say 1 centimeter represents maybe 5 newtons. So you'll measure off this tension T, this angle will be 55 degrees. I think I need to do this for many students because I know there are students who can't do this. Okay, so I'm going to do this here in the space provided. I'm going to just draw this triangle to scale where the weight is downwards 25 newtons. On the 25 I measured off an angle of 35 degrees. Then where the 25 stops I measure off an angle of 55 degrees. Then where these lines meet, I will just measure the length of this line to be t. Okay, so this is going to be a vertical line. I'm using 1 centimeter to represent 5 newtons. So it means 25 newtons is going to be represented by 5 centimeters. So on my vertical line, I'm measuring off 5 centimeters. So let's say starting from here, 5 centimeters stops around here. So I'm going to bring a protractor and measure off 35 degrees to get R. So the 0 is on the vertical, I'm measuring off 35 degrees. The 0 of the protractor is along the vertical and 35 degrees is around here. So I'm going to draw a line for 35 degrees. So that is 35 degrees. Remember this was downwards 25 newtons. This was R. And then from the vertical I'm measuring 55 degrees because we have seen that if I prolong the tension downwards, it makes an angle of 55 degrees with the vertical. So I measure 55 from the vertical. The 0 is along the vertical, but I'm counting from the bottom. So the 0 is along the vertical, 55 is here. 55 is around there. It's not easy to draw on a computer. But when I get instruments, I'll download instruments, I'll use them very accurately. So this is going to be at the tension without changing the direction. The tension is there. So how do I measure? How do I find the T? I measure from here up to where they meet. Then I multiply by the scale. So that is the tension. The tension is going to be represented by the length. I'm measuring the length representing the tension. This is 1, 2, 0.9. It is 2.8. So this is 2.8 times the scale, which is 5. So 2.8 times 5, I'm getting 14. So by scale, I'm getting 14 newtons. And I think that is going to be accepted. That will be accepted. There will be an allowance for using the scale. Okay, so I've showed you three methods. The first one, we resolved the weight. The second one, we resolved the R and T in both the horizontal and the vertical. The third one, I'm drawing the scale diagram. So you can choose the one which is easier for you. Okay, state what is meant by the center of gravity. So now we know that the center of gravity is the point at which all the weight of the body may be considered to act. That's what we call the center of gravity. Point where all the weight of the body may be considered to act, that is center of gravity. A uniform rectangular sheet of card of weight W is suspended from a wooden rod. The card is held to one side as shown. On the figure, mark and label with the letter C the position of the center of gravity of the card. So center of gravity, since the card is uniform and rectangular, we can predict the center of gravity by maybe drawing lines. We can draw lines with a pencil, lines of symmetry. So I'm drawing using my pencil, lines of symmetry, so that I can predict where the center of gravity could be. I'll just draw two lines of symmetry. So it means the center of gravity is going to be somewhere there. So that is C. Okay. Mark with an arrow W the weight of the card. Of course, weight acts vertical downwards through the center of gravity. So I would draw a vertical line through the center of my center of gravity. And I think the vertical line is close to this point. So this is going to be the vertical line which shows the center of gravity, that is W. Okay. The card in B is released, the card swings on the rod and eventually comes to rest. It swings and eventually comes to rest. List the two forces other than weight and air resistance that act on the card during the time that it is swinging. State where the force acts. State where the force acts. Okay. So when the card is released, it swings. There is a friction at this part here of contact with the rod. So that is one force. There's also normal reaction at the same point of contact. Where the card is in contact with the rod, there is friction. Where the card is in contact with the rod, there must be normal reaction force. Normal reaction force always acts at 2 points of contact, at point of contact. So one, we have friction between the card and the rod. Friction between the card and the rod. That's number one. Number two, there is normal reaction force. Normal reaction force. normal reaction force, which could be actually upwards because the weight is downwards. Normal reaction force upwards at the rod. Those are the two forces acting. I don't think there is any other force acting apart from those two. By reference to the completed diagram of figure 3.1, state the position in which the card comes to rest. Explain why the card comes to rest in this position. So when the card is released, of course, it is going to swing in this direction. It has a moment due to this weight. And it will come to rest when the point C is just vertically below the rod. That is when it will come to equilibrium. Because at that point, when C is just below the rod, it means the weight will not have any moment. In other words, it will come to rest when it is somewhere here. It will come to rest when I think this it will be somehow like this. The end where it is being held will actually be the one which is going to be vertically below C. So it will come to equilibrium when the center of gravity is just below the rod, or when the vertical line through the center of gravity is just under the rod. Therefore, briefly explain why the card comes to rest in this position. So we say it comes to rest with the line of action of the weight acting through the rod. It comes to rest with the line of action of the weight acting through the rod. In other words, the line of action will be through the rod. In other words, in simple terms, I'm saying C, when C is vertically below the rod. When C is vertically below the rod, so that the weight does not have a moment about the rod, so that the weight does not have a moment about the rod. So when the center of gravity is just below the rod, it means the weight is acting through the vertical line through the center of gravity, where that is where the weight, the entire weight is considered to act is through the rod. It means the perpendicular distance of the weight from the rod, which is acting as the pivot, would be 0. So there will be no moment caused by the weight of the card. At that point, it will come to equilibrium. Define density. Density is mass divided by volume. Explain how the difference in the densities of solids, liquids, and gases may be related to the spacing of their molecules. This could be an A-level question now in the unit called temperature, ideal gases, and thermal properties, but we can still answer it here. How is the density related to the spacing of the molecules? We know that the density of liquids and solids is almost of the same order. The density of solids is just twice, but the power of 10 is going to be the same. So we can say density of solids, of liquids and solids, density of liquids and solids is of the same order. because the spacing is almost the same. As the spacing is almost the same, is almost similar. Or the spacing of, by the way, the spacing of liquids is almost just twice that of solids. That is almost same because the order, the power of 10 will be the same. The density of liquids and solids is of the same order as the spacing is almost similar. But the density of the gases is going to be much smaller. Density of gases is much less. Reason, the spacing is much more. As the spacing is much more. Okay, because the spacing of molecules in gases is greater, the density of gases is going to be smaller. The density of liquids and solids is almost the same because their spacing is relatively the same. But that of gases is going to be much smaller than that of solids and liquids. A paving slab, it has a mass of 68 kilograms, 50 millimeters by 600 by 900. Calculate the density of the material from which the paving slab is made. So we already know that density is mass divided by volume. The mass is 68 kilograms. The volume, they have given us dimensions. These ones are in millimeters, so we have to multiply each of them by 10 power negative 3, 10 power negative 3, 10 power negative 3 to get the in meters cubed. So this will be 50 times 10 power negative 3, 600 times 10 power negative 3, 900 times 10 power negative 3, which will give us, let's check, 50 exponent negative 3 times 600 exponent negative 3 times 900 exponent negative 3. So I'll get 68 divided by the answer, which is 251, 2518, 2518, which is approximately 2520 or 2500. Calculate the maximum pressure a slab could exert on the ground when resting on one of its faces. Maximum pressure, that is the greatest pressure, is exerted when the area is smallest. So pressure is maximum when the area is the smallest. From these dimensions, we notice that to get the smallest area, we can multiply 50 by 600. That is the smallest area. Therefore, we shall substitute the force is the weight. This is going to be mg over the smallest area. So mg, that is 68 times 9.81 divided by the area. The smallest area is going to be 50 times 10 power negative 3 times 600 times 10 power negative 3. I multiply by 10 power negative 3 to change the dimensions to meters. So this is 500 exponent negative 3, sorry, 50 exponent negative 3 times 600 exponent negative 3. Then I will have 68 times 9.81 divided by the answer, which is 22236. 22236, or approximately 2.2 times 10 power 4 pascals. Define torque of a couple. Remember, a couple constitutes two forces which are equal in magnitude but in opposite directions, whose lines of action will never meet. So this is the product of one of the force, product of one of the force, or I mean one of the forces. and the perpendicular distance between the forces, and the perpendicular distance between the forces. Product of one of the forces and the perpendicular distance between the forces. That is the torque of a couple. A uniform rod of length 1.5 meters and weight 2.4 newtons is shown in the figure there. So you can see the figure. The rod is supported on a pin passing through a hole in its center. Ropes A and B provide equal and opposite forces of 8 newtons. So this is going to act as the position of the pivot. So B is causing clockwise moments, A is causing clockwise moments, so the beam must be rotating clockwise. Calculate the torque on the rod produced by ropes A and B. So the torque or moment is equal to the force, which is 8 newtons, times the perpendicular distance between the two, which is 1.5. Product of one of the forces and the perpendicular distance between them, that's 1.5. I think that is 12. Or you would get the moment caused by this rope times its distance from here, which is 7.5, plus the moment caused by the other one plus its distance, which is 7.5. 2.4 newtons has no moment about the pin because its line of action is through the pin. Discuss briefly whether the rod is in equilibrium. It cannot be in equilibrium. It is rotating anti-clockwise. It is rotating clockwise. So there is a resultant moment. There is a resultant moment, or I will use a resultant torque. There's a resultant moment or resultant torque. So the sum of moments is not zero. Sum of moments is not zero. So the rod, we see that the rod rotates clockwise. So the rod rotates, and since it rotates, it's not in equilibrium. So the rod rotates and is not in equilibrium. The rod in B is removed from the pin and supported by ropes A and B as shown. Rope A is now at point P, 0.3 meters from the other end, from one end of the rod, and rope B is at the other end. Calculate the tension in rope B. Calculate the tension in rope B. So since we want the tension in rope B, we shall take moments at point P. And if we take moments at point P, this was the weight, and the distance from the end to the other one is 0.75. This is 0.75. So it means we subtract 0.75 minus 0.3, which gives us 0.45. So this distance is 0.45. And that means the distance of the rope A from the fixed point is 1.5 minus 0.3, which is 1.2. So we are taking moments about P. Moments about P. So clockwise we have the weight only. So the weight of 2.4 newtons times its perpendicular distance, which is 0.45, should be equal to the moment caused by rope B, which I will call the tension or the force of B, FB, times its perpendicular distance, which is 1.2. So this will give us FB. Let's find FB. 2.4 times 0.45 divided by 1.2. So that is 0.90. So this is 0.90. Calculate the tension in rope A. Tension in rope A. So the total forces upwards should be equal to total forces downwards if the beam is in equilibrium. So the tension in rope A plus the force in B should be equal to the weight downwards. So the tension in A should be equal to the weight, which is 2.4 minus the 0.90. 2.4 minus the answer, which is 1.5. That's 1.5 newtons. Distinguish between scalars and vectors. Of course, we know scalars have magnitude only. Vectors have both magnitude and direction. Scalars have magnitude. By the magnitude is the same as size. Scalars have magnitude only or size only. And vectors have both. Vectors have both magnitude and direction. Underline all the vectors, the vector quantities in the list. I said vector quantities are 6 for your level. In kinematics, you will find velocity, acceleration, and displacement. In dynamics, you'll find momentum or force. Those are 5. Then you'll find moment. I think moment is the 6th one. So we have acceleration and momentum. They said vectors plus the weight, because weight is a force. A force of 7.5 newtons acts at 40 degrees to the horizontal as shown here. Calculate the component of the force that acts horizontally. So we resolve 7.5 in the horizontal. That will be 7.5 cos of 40. 7.5 cos 40, 7.5 cos of 40. That is 5.75. 5.75. It is not 5.8 because the figure is 5.745. You can't round off this to 5.78. It is either 5.7 or 5.75, not 5.8. It is either this, that, or this one here. Because the digit next to 7 is 4. You can't round it off to 8. Then we resolve vertically. We take 7.5 to the vertical. That will be sine. So this will be 7.5 sine of 40. 7.5 sine 40. No, yes, sine 40. That is 4.82. 4.82. Two strings support a rod of weight 7.5 newtons as shown in the figure. One string has tension T1 and is at an angle of 50. The other has T2 at an angle of 40. The object is in equilibrium. That means the resultant force is going to be 0. Determine the values of T1 and T2 by using a vector triangle or by resolving. I will begin by resolving. So if I resolve, T1 to the horizontal will point to the left and to be T1 cos 50. T2 will point to the right hand to be T2 cos 40. So for equilibrium, T1 cos 50 must be equal to T2 cos 40. That's number one. So for equilibrium, T1 cos 50 is equal to T2 cos 40, meaning T1 is equal to T2 cos 40 divided by cos 50. That is one equation. Then let's check in the vertical. So I am going to resolve also in the vertical. T1 taking it to the vertical will be T1 sine 50. T2 taking it to the vertical will be T2 sine of 40. These two will point upwards, so I will sum them up. So I have T1 sine 50 plus T2 sine 40 must be equal to the downward force, which is 7.5 newtons. So I'm going to substitute for T1 with this equation here. So this will be T2 cos 40 over cos 50. Multiply this by sine 50 plus T2 sine 40 is equal to 7.5. So I'll put this in a calculator. On the left hand side, I have cos of 40 times sine of 50 divided by cos of 50 plus sine of 40. Then I divide this quantity with 7.5 by that quantity. So I'm saying 7.5 divided by the answer. I was making T2 the subject. So you notice that T2 is equal to 4.82. That is T2. Then I can find T1 by substituting. So T1 is equal to 4.82 times cos 40 divided by cos 50. So we can check this. The answer times cos 40 divided by cos 50. So I have 5.75. So T1 is 5.75. So this will be 5.75 and this is 4.82 newtons. I have done that by resolving. Let's check by a triangle. When they say by triangle, you can use the cosine rule if it is possible, or you can use the sine rule if it is possible, or you can use because you will have drawn a vector triangle, you can still use a scale diagram. So I'm going to use a scale diagram, but I'll first of all extract out the triangle. Let me use a pencil to draw a triangle. In the vertical, I would have drawn the triangle on the same diagram, but I want to maintain the diagram for resolving. So in the vertical, I have 7.5 vertically downwards. Then 7.5, the force T1 makes an angle of 40 degrees with 7.5. So I'll consider 40 degrees to the vertical to arrive at T1. That is T1. It makes an angle of 40 degrees with the vertical because this is 50, the other one is 40. So T1 makes 40 degrees with the vertical. Then how about T2? When I prolong T2 downwards, we notice that T2 makes this angle here with the vertical, or from the vertical. And this angle here, if this is 40, this is 40, this angle is 50. So T2 will make an angle of 50 degrees. So this will be T2. It makes an angle of 50 degrees with the vertical. So those vectors will meet. So I'm going to draw this triangle to scale. And I will say 1 centimeter represents 7.5. 1 centimeter represents 1 Newton. So I'm doing this by scale. I would use the space here. Since they didn't tell us to draw on the diagram, so I'll use this space. So that was method 1. Now method 2. So I'm saying my scale, 1 centimeter is going to represent 1 Newton. I hope 7.5 can fit in this space. So I will begin by drawing a vertical line of 7.5 centimeters. I hope it fits. I think it will. So I will draw a vertical line, perfectly vertical. On this line, I'm going to only measure 7.5. So I will start from this point so that I measure 7.5. And I see 7.5 stops here. Where 7.5 stops, I'll put a protractor to measure 40 degrees. Remember, I'm drawing this small triangle to scale. I'm drawing the small triangle to scale, so I'm putting a protractor with a 0 along the vertical. So 40 degrees, I think 40 is here. So I've located the 40. So that is the line for 40 degrees. This angle here is 40. So this is going to be, this was 7.5 newtons. This is going to be T1. Then from the vertical, remember I'm putting this triangle to scale, where this angle is 50 degrees. So I will measure 50 again from the vertical, but downwards. The 0 is at the bottom. So I'm measuring 50 degrees. So 50 degrees is somewhere there. So this is 50 degrees. So this points in that direction. That is T2. This angle here is 50 degrees. So when you draw to scale, you don't need to calculate anything. You know the scale, 1 centimeter is 1 Newton. So I'll just measure the length. For T1, I'll just measure the length of the line where they meet from this point here, this point where they meet. And this is 5.5678. So T1 is 5.8. That is from scale. Then T2, I'll measure T2 by measuring the line. It is T2 is 4.8. So these values are from scale. And notice that they are not very far away from those ones which are calculated by resolving. So you can choose which method is easier for you. You can choose which method is easier for you. Okay, define pressure. Pressure is not any force. Pressure is the force acting normally. The force must be acting perpendicularly. So pressure is the force acting normally per unit area. Force, to change the color. The force acting normal. The force must be acting at right angles. The force acting normally per unit area. That is pressure. The force acting normally per unit area. Explain in terms of the air molecules why the pressure at the top of the mountain is less than that at the sea level. Of course, pressure depends on these air molecules. And pressure is exerted when the air molecules collide and bounce off or rebound. That is when there is a change in momentum. I want you to notice that in geography or other subjects, you must have mentioned that the higher you go, the cooler it becomes. It means that the temperature is less on top of the mountain than at the bottom of the mountain. And if the temperature is less, it means the average speed of the molecules on top of the mountain is lower than that at sea level. That means the change in momentum for these molecules when they collide with the surfaces is going to be smaller on top of a mountain. Also, you could think about there being fewer molecules per unit volume on top of a mountain than at sea level. Okay, so we can say when molecules collide with the surface and rebound, there is a change in momentum. There is a change in momentum. There's a change in momentum, hence, because there's a change in the momentum, they exert a force, hence exert a force. Hence they exert a force. However, the temperature is less on top of a mountain. The temperature is less on top of a mountain. Thus, the speed of molecules is lower. Thus, the speed of molecules is less or is lower. Thus, the speed of molecules is lower, hence less pressure. So, because of the molecules, the temperature is small, it means the speed of the molecules is also smaller or it is lower. That would mean that since the average speed is smaller, it means the change in momentum they experience when they collide with the surface is small. Hence, it means they would exert less pressure. Also, you would think about when a molecule collides, when molecules collide with the surface and rebound, there is a change in momentum. However, instead of talking about the temperature being less, you would talk about there being fewer molecules per unit volume on top of a mountain. Or I would say there are fewer molecules. There are fewer molecules per unit volume. There are fewer molecules per unit volume on top of a mountain, hence less pressure on top of a mountain, hence less pressure. There are fewer molecules per unit volume, hence less pressure. So that is another alternative. Instead of talking about the temperature at the top of the mountain being less, you can talk about, you can explain in terms of the number of molecules on top of a mountain. There are fewer molecules on top of a mountain, hence less pressure. Okay. The figure shows a liquid in a cylinder. The cross-sectional area of the container is 0.45 meters squared. The height of the column of liquid is 0.25 meters and the density of the liquid is 13,600. Calculate the weight of the column of the liquid. So the weight is going to be m times g. And the mass is going to be density times volume. Then we shall multiply that by g. So we can now find the weight. So the weight is going to be density, which is 13,600 times V. Volume is going to be the cross-sectional area. So let me first add there G 9.81 times the volume, which is the cross-sectional area, times another length or the height. So that would be 0.450 times 0.25. So that is 13,600 times 9.81 times 0.45 times 0.25. So that gives us 15,000. It is 15,009.3. So I'll just take 15,000. So this is 15,000 newtons. Calculate the pressure on the base of the container caused by the weight of the liquid. Pressure is equal to the force over area, which will be actually the weight divided by the area, which is 15,000 divided by the area, which is 0.45. So that is answer divided by 0.45, which is 3.3 times 10 power 4. So that is 3.3 times 10 power 4. Alternatively, you would find the pressure due to the liquid as H rho G. The height is 0.25. Density is 13,600. G is 9.81. You would arrive at the same answer, 3.3 times 10 power 4. Explain why the pressure exerted on the base of the container is different from the value calculated in Roman 2. So we have been getting we have got the pressure using the weight of the liquid, but the container itself also has a mass. The container itself has a mass. Also, there is air pressure because this was cross-sectional area of the container, the height of the column of the liquid. So we're actually finding the weight of the liquid. How about the container? Also, if I ignore the container's mass, then how about the atmospheric pressure? To be precise, the atmospheric pressure is the most important thing here. So explain why the pressure exerted on the base of the container is different from the value calculated in Roman 2. So pressure will be greater due to air pressure or atmospheric pressure acting on the surface of the liquid. Pressure will be greater due to air pressure or atmospheric pressure. Due to air pressure acting on the surface of the liquid. The pressure will be greater due to air pressure acting on the surface of the liquid. Define torque of a couple. We have seen a couple, those are two forces, parallel and the opposite with equal magnitude. Their lines of action never meet. So a couple is the product, torque of a couple, moment of a couple. The word torque is referred to moment. So this is product of one of the forces and perpendicular distance between the two forces. So that is moment of a couple. A wheel is supported by a pin at its center of gravity as shown in the figure here. Okay, so its center of gravity is at P. That means the weight of the wheel must be downwards at P. At that point where there is a pin, the pin might exert an upward force, which we call the normal reaction, onto the wheel upwards. The plane of the wheel is vertical. The wheel has radius 25 centimeters. Two parallel forces 35 newtons act at the edge of the wheel in the vertical directions as shown. Friction between the pin and the wheel is negligible. List two other forces. They have said the friction is negligible. You can't list the friction again. State the direction of these forces and where they act. Number one, I've said the weight. The weight of the wheel at P, vertically downwards. Because they said state the force, the direction, and where they act. So weight at P vertically downwards. Then number two is the normal reaction at P again. Normal reaction at P. That is at the point of contact. Point of contact with the pin. With the pin, and that one is vertically down, vertically upwards. I think those are the two forces. I don't think there's any other. Calculate the torque of the couple. Remember, the torque is the product of one of the forces and the perpendicular distance between them. So torque, one of the forces is 35, perpendicular distance between them. Since the radius of the wheel is 25, it means the perpendicular distance is twice the radius, which is the diameter, that is 50. Or it will be 0.25 times 2, which will be 35 times 0.25 times 2, which is 17.5. So this is 17.5, or you can write 18 Newton meters. The resultant force on the wheel is 0. Explain by reference to the four forces acting on the wheel how it is possible that the resultant force is 0. We have seen even the directions. The two forces acting, the normal reaction plus 35 upwards should be equal to the weight downwards plus the other force downwards. So the two 35 Newton forces are equal and opposite. Are equal and opposite. Explain by reference to the four forces acting on the wheel how it is possible that the resultant force is 0. So we are saying the two 35 forces, 35 Newton forces are equal and opposite. The weight and the normal reaction the weight and normal reaction are also equal and opposite. So it means the resultant force is going to be 0. Weight and normal reaction are also equal but opposite. So the resultant force is going to be 0. State and explain whether the wheel is in equilibrium. Already there is a resultant torque, so it cannot be in equilibrium. So not in equilibrium as the resultant torque is not 0. not in equilibrium, as the resultant torque is not zero. Okay. The cylindrical disc is shown in the figure 1.1. The disc has diameter 28 millimeters, thickness 12 millimeters. The material has density 6.8 exponent 3. Calculate to two significant figures, the weight of the disc. So we want the weight. Weight is going to be m times g. The mass is density times volume. So it will be density times volume times g. But the volume is cross-sectional area times height h. So the volume is, this is going to be density times pi r squared h, that is the volume, then times g. So we have the diameter, so the radius is 14. I'll just use the radius, 14 times 10 power negative 3 meters. Then h is 12, so that will be 12 times 10 power negative 3 meters. I think that is all. So we can now substitute. So the weight is going to be equal to the density, which is 6.8 times 10 power 3, then times g, which is 9.81. Now we are multiplying by the volume, which is pi. Radius is 14 times 10 power negative 3, but this is squared, then times the h, which is 12 times 10 power negative 3. So we just press our calculator once and for all. So 6.8 exponent 3 times 9.81 times pi times 14 exponent negative 2 negative 3 squared times 12 exponent negative 3. So that is 0.49. So the weight is 0.49. Define pressure. So we now know that pressure is the force acting normally. Force acting normally per unit area. Normally here is meaning the force must be acting at right angles, that is perpendicularly. A cylinder is placed on a horizontal surface as shown here. The mass is given as 5.0 plus or minus 0.01. 9.4 is the diameter plus or minus 0.1. Calculate the pressure produced on the cylinder. Pressure produced on the cylinder. So pressure is equal to the force over area. The force will be the weight, which is mg divided by the area. And of course, we know that the area is going to be equal to pi r squared, which is pi d squared over 4, because they have given us the diameter. So it means the pressure is going to be equal to, I'm substituting for area, so it will be 4 mg divided by pi d squared. So I'm now substituting. That will be 4 times the mass, 5.09, times g, which is 9.81, divided by area, which is pi, times d. D is 9.4 times 10 power negative 2, and that is squared. So 4 times 5.09 times 9.81 divided by pi divided by 9.4 exponent negative 2, close the brackets, squared. That is 7195. 7195. 7195 pascals. That is the pressure. Calculate the actual uncertainty in the pressure. They have given us, we have that pressure is equal to 4 mg divided by pi d squared. It is better to express the expression for pressure in terms of the quantities whose uncertainties have been given. So pressure, since we have multiplication and division, G is constant, 4 pi, those are constants. I'll only deal with quantities whose uncertainties have been given. So the absolute uncertainty in pressure divided by the actual pressure is equal to uncertainty in mass divided by the mass plus twice the absolute in diameter divided by the diameter. So the actual uncertainty in pressure is going to be for mass. The absolute in mass is 0.01 divided by 5.09 plus 2 times for diameter 0.1 divided by 9.4 times the density, which is times the pressure, which is 7195. So that will be the actual. So this is, I will open the bracket, 0.01 divided by 5.09 plus, open another bracket, that is 0.2. I multiply 2 by 0.1, which is 0.2 divided by 9.4. So answer times 7195. So I have 167. The absolute is 167 or 170 or 200. So this is 167. Then state the pressure with its actual uncertainty. So I'll round off this. Absolute uncertainty in pressure is 167, which is approximately 200 to one significant figure. It is ending with the 2 zeros, so I'll write my answer ending with the 2 zeros. So this is 200. So this will be 7,200. So that will be the correct way of writing the answer. Force is a vector quantity. State 3 other vector quantities. So we said there are basically 6 vector quantities. Apart from force, I can't mention weight again because weight is a force, but I can go to moment. There is momentum, there is velocity, there is acceleration, there is displacement. Those are the 6 vector quantities together with the force that you may interact with at AS level. Of course, there are others in A level such as gravitational field strength, magnetic field strength, and so on and so forth. Okay. 3 coplanar forces X, Y, and Z act on an object as shown in the figure. The force Z is vertical and X is horizontal. The force Y is at an angle theta to the horizontal. The force Z is kept at 70 newtons. So this is always 70 newtons. In an experiment, the magnitude of X is varied. The magnitude and direction of Y are adjusted so that the object remains in equilibrium. The figure shows the variation of the magnitude of force Y with the magnitude of force X. So let's see the figure. So that is the figure showing variation of Y with X. Okay, so that is the graph. X varies from 0 to 120, Y varies from 50. Let us use the figure to estimate the magnitude of Y for X equals to 0. So for X equals to 0, we just prolong this curve. You see it is becoming a curve, so I think it is touching here. If you try to to extend the curve, it is touching there, so that is 70. When x is 0, y is 70. State and explain the value of theta for x equals to 0. So let's go back to the diagram. For x equals to 0, if x is equal to 0, remember y is 70. For x equals to 0, y is 70. Let's find theta. We can use mathematical terms such as this is 70 in the vertical, this is 70 in the hypotenuse. Opposite hypotenuse, that is sine. So sine of theta is equal to 70 over 70. 70 over 70, that gives you theta as sine inverse of 1, which is 90 degrees. So you can use mathematics because at x equals to 0, y is 70 newtons. And we have already seen that z is always kept at 70. So in the vertical you have 70, in the hypotenuse you have 70. Sine theta is 70 over 70, which makes theta to be 90 degrees. Or by common sense, you can see if x is 0, it means there is no force, there is no result, there is no force in the horizontal. So it means y cannot be acting or cannot have a component in the horizontal if x is 0 for the body to remain in equilibrium. It means y must be acting vertically upwards so that it balances z downwards. That makes theta to go to 90 degrees. So state and explain the value of theta for x equals to 0. So I'm saying you can explain this by calculation, that sine theta is equal to z over y, which is equal to 70 over 70, which makes sine theta to be equal to 1, which makes theta as 90 degrees. That is fine. You can explain in terms of this calculation. However, so theta is equal to 90 degrees because for equilibrium, the direction of y must be opposite to z. The direction of y must be opposite to z. Must be opposite to z when x is 0. So when x is 0, it means there should be no any other force acting in the horizontal if the body is in equilibrium. Then part 3, the magnitude of x is increased up to 160 newtons. Use resolution of forces to calculate the value of theta. So we have something like this. So this is always 70, this is 160 newtons, this angle is theta, this is y, and this is the horizontal plane. So they are saying we use resolution of forces. Use resolution of forces to calculate the value of angle theta. So, so I'm going to resolve y in the horizontal first. That will be y cos theta. That should be equal to 160 in the horizontal. I will resolve y in the vertical. In the vertical, I take it to the vertical. That will be y sine theta, and that will be equal to 70. So I divide the two equations. Y sine theta divided by y cos theta, that is tan theta, is equal to 70 over 160. What is theta? So theta is going to be the tan inverse of 70 divided by 160. So shift tan inverse of 70 divided by 160, that is 23.6, which is approximately 24 degrees. Then the magnitude of y, of force y. So we just go back and substitute for theta in one of those equations. So I would say y is equal to or y sine theta is equal to 70. So y is going to be 70 divided by sine of 23.6. So 70 divided by the sine of the answer. So that is 174.6, which is approximately 175. The angle theta decreases as x increases. Explain why the object cannot be in equilibrium for x equals to 0. Theta decreases as x increases. Explain why the object cannot be in equilibrium for theta equals to 0. So it means if theta is 0, this is x, there is z there, this is x, there is z. So it means y will be in this direction. When theta is 0, y is in the horizontal. So it means the z will not have any force to balance it. So the body cannot be in equilibrium. So equilibrium is not possible as there is no vertical component of y to balance z. Equilibrium, when theta is 0, equilibrium is not possible. Equilibrium is not possible as there is no vertical component from y to balance z. Equilibrium will not be possible since there is no vertical component coming from y to try and balance z. The figure shows a metal cylinder of height 4.5 centimeters and base 24 centimeters squared. The density of the metal is 7,900. Show that the mass of the cylinder is 0.85. So we know that density is mass over volume. Mass is density times volume. So this is going to be density, which is 7,900 times the volume, which is volume is cross-sectional area times height. Cross-sectional area is 24, but is power times, it is in centimeters squared, so that's 24 times 24. Okay, if it is hard to convert, you can say 24 centimeters times centimeters, which is 24 times 10 power negative 2. 24 times 10 power negative 2 to change it to meters, times again 10 times 10 power negative 2, that is for 1 centimeter, into meters. That is changing centimeters squared to meters squared. So this will be 24 times 10 power negative 4 meters squared. So the area is 24 times 10 power negative 4. Then times the height, because volume is cross-sectional area, times height. So this will be times 4.5 times 10 power negative 2 again. So let's check the mass. 7,900 times 24 exponent negative 4 times 4.5 exponent negative 2. So that is 0.853. 0.8532, which is approximately 0.85 as required. The cylinder is placed on a plank as shown in the figure. The plank is at an angle of 40 degrees to the horizontal. Calculate the pressure on the plank due to the cylinder. So pressure acts is due to the force that acts normally. So we need to find the vertical force which makes 90 degrees with the plank. So I'll put a ruler. One, we know that the weight of the cylinder acts vertically downwards. So I'll begin by drawing a vertical line downwards, that is for the weight. So this is for the weight, that is W. But the force which exerts pressure on the plank must be acting at 90 degrees. So I'll draw another vertical line which makes 90 degrees with the plank. So vertically upwards, that's the normal reaction. And vertically downwards, making an angle of 90 degrees is going to be the component of weight. You and me note that this angle here is 40 degrees. Remember, this is 90. So this will be W cos of 40. If we were to resolve parallel to the plane, that is downwards. In case the cylinder slides downwards, this will be W sine of 40. Let's now see the question. The question wants us to calculate the pressure. So pressure is force over area, but note that the force is that one which acts at 90 degrees. So the pressure is equal to the force over area, which force is going to be the weight W cos of 40 over the area, which area was given as 24 centimeters squared. So this will be over area. This is going to be weight is 0. They gave us the mass as 0.85, so the weight is mg. So that is going to be 0.85 times 9.81 cos of 40 divided by area. The area was 25 centimeters squared, so that is 24 times 10 power negative 4 to change it to meters squared. So this should be the pressure it exerts. 0.85 times 9.81 cos of 40 divided by 24 exponent negative 4. So that is 2661, which could be approximately 2.7 times 10 power 3. 2.7 times 10 power 3 in pascals. The cylinder then slides down the plank with a constant acceleration of 3.8 meters per second. A constant frictional force F acts on the cylinder. Calculate the frictional force. Like I said, the force which is going to make this move downwards is W sine 40, but there is a constant frictional force upwards. I'll call that Fr. From Newton's second law, the resultant force F is equal to mass times acceleration, which will be the difference. That is W sine 40 minus the frictional force Fr. So, resultant force F by Newton's second law is mass times acceleration. And the resultant force is the weight, which is W sine 40 minus the frictional force F should be equal to the mass times the acceleration. So the weight is 0.85 times 9.81. That is sine of 40 minus the frictional force F. This is going to be 0.85 times the acceleration, which is 3.8. So I'm going to just collect like terms to find F. F is going to be equal to, I take F the other side, so I have 0.85 times 9.81 sine of 40, then minus, I open the brackets, 0.85 times 3.8. So it means F is 2.13. 2.13 newtons. Okay, define moment of a force. So we have seen that the moment of a force is the product of the force, and the perpendicular distance of the line of action of force to the pivot, of line of action of force to the pivot. Okay, an arrangement for lifting heavy loads is shown in the figure. A uniform metal beam AB is pivoted on a vertical wall at A. The beam is supported by a wire joining end B to the wall at C. The beam makes an angle of 30 degrees as we see in the diagram with the wall, and the wire makes an angle of 60 degrees with the wall. The beam has length 2.8 meters and weight 500 newtons. The beam is uniform, its weight is at the midpoint. That means the distance from where the beam stops, from the center of the beam to the end A is going to be 1.4. That distance is 1.4 meters. The other one is also 1.4 meters. The beam is in equilibrium, meaning resultant moment, resultant force, they are zero. By taking moments about A, show that T is 2.1 kilonewtons. Let's look at A. So 500 newtons causes clockwise, 4,000 causes clockwise. Then we shall look for the vertical component of T, because if we take T, which means we shall again look for the perpendicular distance of T from the pivot. But if we resolve T vertically, it means its perpendicular distance is going to be the same as that of the 4,000. So let's look for, or by the way, T is acting at 90 degrees at the end of the rod. So its perpendicular distance from A is already found there. So that is fine. All we shall need is the perpendicular distance of 500 and 4,000. And T is causing a moment which is in that direction, that is anti-clockwise. So T times the perpendicular distance, which is 2.8, should be equal to, let's begin with the 500. What is its perpendicular distance? So 500, the perpendicular distance is this one here, which is the same as that one there. So you have a triangle like this one, where this is 1.4, this angle is 30. Let me make it bigger. You have a triangle here, where this distance is 1.4 meters, and this angle is 30, and you want this distance here. So that is opposite hypotenuse, that is sine. So sine 30 is equal to opposite over hypotenuse. That means the perpendicular distance is 1.4 sine 30. So this is 1.4 sine of 30. We are going to repeat the same for 4,000. We have the perpendicular distance is this one here, which is the same as that one on top here. So we have a triangle like that one, where this distance is 2.8 meters for 4,000. And this is the distance I want. This angle is still 30. So that distance is now 2.8 sine of 30. So this is plus 4,000 times 2.8 sine of 30. So we now press our calculator and verify. So I have 500 times 1.4 sine of 30 plus 4,000 times 2.8 sine of 30, then divide by, we have 2.8 on the left hand side, divide by 2.8. So that is 2,125. So T is 2,125 newtons, which is approximately 2.1 times 10 power 3 newtons, or 2.1 kilonewtons. Calculate the vertical component TV of the tension T. So we resolve T in the vertical. To resolve T in the vertical is easy. We shall just need this angle here. And this angle here is 60 degrees because it is the same as this one. If I draw a vertical line here, taking T to the vertical, it will be T cos of 60. So that is T cos 60. So that is T cos 60, which is equal to 2,100, that is the tension, cos of 60. So we say T cos 60, 2,100 cos 60. So that is 1050. 1050 newtons, or 1100. State and explain why TV does not equal the sum of the load and the weight of the beam, although the beam is in equilibrium. So when you add a TV, when you look at TV upwards, it is 1050. That is the vertical component is 1050. But when you look at the sum downwards, it is 4,500. It means there must be another force at point A. There must be another force at point A, which should be acting upwards. There must be a force on the rod to balance, to combine with the tension upwards, the vertical force upwards, to balance with the weight downwards. So we can say there is an upward vertical component of force at A. There is an upward vertical component of force at A, so that upward force at A plus TV, so that the upward force at A plus TV should be equal to the sum of downward forces. That is the weight plus the load. So there must be an upward vertical component of force at this point here. There must be a vertical component at point A, so that when we sum up that vertical component plus the component TV, it should be balancing with the weight plus the load which has been added. Okay. State two conditions for a body to be in equilibrium. I think those conditions we are now aware of them. Number one, the resultant force in any direction is 0. The resultant force in any direction is 0. The resultant moment about resultant torque. When I say moment, I can also mean torque. About any point is also 0. That is for a body to be in equilibrium. A uniform beam AC is attached to a vertical wall at end A. The beam is held horizontal by a rigid bar BD. So the beam is horizontal. I'll first prolong this. I'll first prolong the length of the bar upwards for easy resolving. So this is 33 newtons. And this angle here is the same as that one. So this angle is 52 degrees. Okay, in case I want to resolve vertically, I will draw a vertical line there. In case I want to resolve vertically, this angle can be 38 degrees. Okay, the beam is in equilibrium. Calculate the vertical component of the force exerted by the bar on the beam. So I want the vertical component of 33. Since I've already simplified it, you can see that the vertical component is going to be 33 sine 52 or 33 cos 38. So the force here is going to be 33 sine 52, or it will be 33 cos 38. 33 cos 38, which is 26.00, so it is 26. By taking moments about A, calculate the weight W. So we are taking moments about A here. So the weight is causing clockwise moment. This load is causing clockwise moment. The horizontal component of this, or we can just take the vertical component which acts upwards, and that is going to be 26 newtons. 26 newtons. That is going to cause anti-clockwise. And of course, the horizontal component will be acting through the beam, so it will cause no moment. So by taking moments about A, we have W times perpendicular distance. Which distance is this one? I think this is half, which is 0.15. So that is it 0.15? No. The beam is 0.3 plus 0.1, that is 0.4. So this is 0.20 meters in the middle. So we have W times 0.2 meters, that is clockwise, plus we have another clockwise moment. So that is plus. We have 12 newtons, perpendicular distance is 0.4 because 12 newtons is at the extreme end. So that is 12 times 0.4. Those ones are causing clockwise moment. They should be equal to the anti-clockwise moment, which is the vertical component is 26 times the perpendicular distance. If I use the vertical component, then the perpendicular distance is going to be 0.3. So this is times 0.3. So 26 times 0.3 minus 12 times 0.4 divided by 0.2. So that is 15. So W is equal to 15. Okay. Define the moment of a force. So we have seen that this is force times perpendicular distance. Force times perpendicular distance of the line of action of a force. to a point or to the pivot. To a point or to the pivot, that is moment. Force times perpendicular distance from the pivot. A thin disk of radius r is supported at its center or by a pin. The disk is supported so that it is vertical. Three forces act in the plane of the disk, as shown in the figure. Two horizontal and opposite forces, each of magnitude 1.2, act at points A and B on the edge of the disk. A force of 6 newtons acts at an angle theta below the horizontal, acts on the midpoint C of a radial line of the disk, as shown in the figure. The disk has negligible weight and is in equilibrium. No negligible weight, it is in equilibrium. Resultant force is 0, resultant moment is 0. State an expression in terms of R for the torque of the couple. Remember, torque of a couple is the product of one of the forces, 1.2 times perpendicular distance between them, which is R plus R, that is twice R. So the moment of a couple is going to be 1.2 times 2R, which is actually going to be 2.4R. So this is the expression they want. Then friction between the disk and the pin is negligible. Determine the angle theta. So since the friction is negligible, we are going to take moments. About the pin. When we resolve 6 newtons to the horizontal, it acts in that direction and it will be 6 cos theta. This will have no moment because its line of action is through the center of is through the pin. But if we resolve it vertically downwards, it is going to be 6 sine of theta, and it has a perpendicular distance from the pivot, which is r over 2. So that one is causing 6 sine theta is causing anti-clockwise moment, yet the couple is causing a clockwise moment. So for equilibrium, they should be equal. So we shall say 6 sine theta times the perpendicular distance, which is r over 2, should be equal to the clockwise moment, which is 2.4r. So r has cancelled out. And you notice that theta is going to be 2 times 2.4 divided by 6 sine inverse. So you have sine inverse of 2 or 4.8 divided by 6. That is 53 degrees. So theta is 53 degrees. State the magnitude of the force of the pin on the disk. Force of the pin on the disk. Because they said the disk has negligible weight and the resultant force due to the couple is 0 and the disk is in equilibrium, it means the only force acting must be the force which is balancing 6.0 newtons in the opposite direction. So it means the force on the pin must be 6.0 newtons. The magnitude of the force of the pin on the disk should also be 6.0 newtons because 6.0 newtons is the only force which is not balanced on the pin. It's the only force which has no counter. So it means the force of the pin on the disk must also be equal to 6.0, but in the opposite direction to 6.0 shown on the diagram. So it is 6.0 for equilibrium. Okay. A spring attached at one end to a fixed point and hangs vertically with a cube attached to the other end. The cube is initially held so that the spring has 0 extension, as shown in the figure. So we have here the cube, weight 4.0, okay, water density 1000, the spring with 0 extension. The cube has weight 4 and sides 5.1, the cube is released and sinks into water as the spring extends. So if the spring extends, there will be a tension in the spring vertically upwards. The cube has a weight vertically downwards. There is also upthrust, which is upwards. The cube reaches equilibrium with its base at a depth of 7.0 centimeters below the surface. The density of water is 1000. Calculate the difference in pressure exerted by the water. So difference in pressure, we now know that difference in pressure is equal to density times G times the difference in height. So the pressure on the top of the cube will be due to that height H1. The pressure at the bottom of the cube will be due to that height H2. But note that H2 minus H1 is the same as 5.1, which is the height of the cube. So I'll just substitute here. Density is 1000 times 9.81 times 5.1 times 10 power negative 2. So I substitute 1000, 9.81, 5.1 exponent negative 2. So that is 500 or 500.31. Use your answer in A to show that the upthrust on the cube is 1.3. We now know that upthrust is equal to the cross-sectional area times the difference in pressure. And the cross-sectional area, because it is a cube, the area is going to be side by side. So that will be 5.1 times 10 power negative 2, that is one side, then squared, that is cross-sectional area, times the change in pressure, which is 500. So I'll just multiply 500.31. So I'll just multiply that times 5.1 exponent negative 2, but this is squared. So that is 1.30, or approximately 1.31, 1.3 as required. Calculate the force exerted on the spring by the cube when it is in equilibrium. When it is in equilibrium, the resultant force is 0. There is tension upwards plus upthrust upwards should be equal to the weight downwards. So I will simply say upthrust plus tension is equal to the weight. So we want to find the force exerted on the spring by the cube, which is the tension. So the tension is going to be the weight. The weight was given as the weight of the cube is 4.0 newtons. We have got the upthrust as the upthrust is 1.3. So this is going to be 4 minus 1.3. And that gives us, I think that is 2.7. The spring obeys Hooke's law and has a spring constant of 30 newtons per meter. Determine the initial height above the water surface of the base of the cube before it is released. The initial height above the water surface of the base of the cube before it is released. It was released. Note that the cube has that weight inside, that the cube is released and sinks into the water as the spring extends. The cube reaches equilibrium with its base at a depth of 7.0 centimeters below the water surface. So the cube is released. So the question is wanting us to determine the initial height above the water surface of the base of the cube, before it was released. So since we now know the tension in the cube, so let's find the height h. So from Hooke's law, the force is equal to K times extension. So the extension is going to be the force divided by the spring constant. So this is 2.7. The tension, the force exerted on the spring by the cube when it is in equilibrium is 2.7, divided by the spring constant, which is 30. So this is giving us the extension. So the extension is going to be 2.7 divided by 30, which is 0.09, which is approximately 9 centimeters. That is the extension. That is the extension of the spring. But we are saying that when it is in equilibrium, it is the base is at a height of 7 centimeters. So it means the height, the initial height above the water surface must have been the difference between those two. So h is going to be 9 centimeters minus 7 centimeters, which is giving us 2 centimeters. So it means the initial height above the water surface of the base of the cube before it was released must have been 2 centimeters. The cube in the water is released from the spring. Determine the initial acceleration of the cube. So acceleration, when we find acceleration, we consider the resultant force divided by the mass. And of course, we know that the mass is equal to the weight over g. The weight of the cube is 4.0 and g is 9.81. So it means the acceleration is going to be the resultant force, which is 2.7, divided by the mass, which is 4.0 divided by 9.81. And this gives us 2.7 divided by 4 divided by 9.81. So that is 6.6. So the acceleration is going to be 6.6 meters per second. 6.62. Describe and explain the variation, if any, of the acceleration of the cube as it sinks in the water. So it is as it is sinking, what is happening? Of course, as it is sinking, its speed is increasing. That means the viscous force must also be increasing in the opposite direction. And of course, the viscous force will continue increasing not until the upthrust is equal to the weight of the object, or upthrust is equal to the weight, and then the viscous force remains constant. At that point, when the upthrust is equal to the weight, it means the acceleration would have become zero, terminal velocity will have been reached. So we say viscous force increases and then becomes constant, and then becomes constant, and then becomes constant when the weight and the upthrust are equal. It becomes constant when the weight and upthrust become equal, so the acceleration decreases to zero. The viscous force will increase until a point when the upthrust and the weight become equal, so it means the acceleration decreases to zero. So that is the variation of the acceleration. In fact, it decreases to zero when terminal velocity is reached. A liquid of density ρ fills a container of that depth. Derive from the definitions of pressure and density the equation pressure equals to h rho v. So that is very easy. By definition, pressure is equal to force over area, which is going to be the weight over the area, which is going to be mg divided by the area. And the mass is equal to density times volume, which volume is equal to cross-sectional area times height h. So it means the pressure is going to be mg, which m is density, area h times g divided by the area, and area cancels. Hence, which means that therefore pressure is equal to h, or density times g times h. As simple as that. From the definition of pressure, pressure is force over area. From the definition of density, density is mass over volume, which gives mass as density times volume. So when we do the algebra, notice that area cancels out. So pressure in fluids is independent of the area. A small solid sphere falls with a constant velocity through the liquid. State the names of the three forces acting on the sphere. So we have a sphere falling with a constant velocity through a liquid. Of course, there must be upthrust. So number one is upthrust. Upthrust force. Upthrust is sometimes called buoyancy. The spelling of buoyancy is always a problem. Upthrust is sometimes called buoyancy force. Number two, the object has weight, so we have weight or gravitational force. Weight is the gravitational force. Because the sphere is moving, because it falls with a constant velocity, it is moving. So there's a viscous force, which is like friction, the viscous force or drag, which is like friction. State a word equation that relates the magnitudes of these forces. Okay. So because it is moving at a constant velocity, let's check. The weight is downwards, the upthrust is upwards. The viscous drag also acts to oppose motion, so this is the drag. So it means the drag plus the upthrust must be equal to the weight. So we can say that weight equals to the upthrust plus the viscous force. Weight equals the upthrust plus the viscous force. State and explain the changes in energy that occur as the sphere falls. Of course, as it is falling, it is losing gravitational potential energy because of decrease in height. It is gaining kinetic energy because of increase in speed. But then there's friction, there's viscous force, so it also gains thermal energy as a result of friction with the water molecules. So there's decrease in gravitational potential energy, decrease in gravitational potential energy due to decrease in height, decrease in gravitational potential energy due to decrease in height. Remember, potential energy is mg what? Mgh. Okay. Then there will be increase in thermal energy, increase in thermal energy, increase in thermal energy due to work done against viscous drag. due to work done against viscous drag or viscous force. So we can say the decrease in gravitational potential energy could be the increase in thermal energy. Because it is moving at a constant speed, I will not talk about kinetic energy here. It moves at a constant speed. So the decrease in gravitational potential energy due to decrease in height is equal to the increase in thermal energy. So I would have said the change in potential energy equals to the gain in thermal energy. That's what it means. Thermal energy is due to viscous force. Work is done against the viscous force. And the change in the potential energy is due to decrease in the height. Okay. So the liquid in the container is liquid L. Liquid M is now added to the container. The two liquids do not mix. The total depth of the liquids is 0.17 meters. The figure shows the pressure P inside the liquids varies with height x above the base of the container. Use the figure to state the value for atmospheric pressure. So when the height is 0, so we look at when the height is 0, the liquid is at a pressure of, liquid M is at a pressure of 9.1 times 10 power 4. So that should be atmospheric pressure. So atmospheric pressure is 9.10 times 10 power 4 pascals. Then determine the density of the liquid. Determine the density of the liquid. So difference in pressure, we know difference in pressure is equal to density times G times difference in height. Let's check the difference in pressure of the two liquids. So we have we have the difference in pressure. This is 9.15 and this is 9.0. So this is from 0.1 up to, I think this is 0.17. So this is the change in pressure. So the change in pressure is going to be 9.15 minus 9.10, but this is times 10 power 4 is equal to the density of the liquid times 9.81 times the difference in the height, which is from 0.1 to 0.15. So this is going to be times, is it 0.15, 0.17? It is 0.17. So that is 0.17 minus 0.10. So we find the density as 9.15 minus 9.1 times 1 exponent 4 divided by, open brackets, 9.81 times, I think 0.17 minus 0.10 is 0.07, 0.07. So that is 729.119942. So that is 728, which is approximately 730. The kilogram, meter, and second are all SI base units. State two other SI base units. We saw this in physical quantities and units. So this is the ampere, the mole, the Kelvin, the candela, all those are SI base units. A uniform beam, a B of length 6 meters, is placed on a horizontal surface and then tilted at an angle of 31 degrees. to the horizontal as shown here. The beam is held in equilibrium by four forces that all act in the same plane. A force 90 newtons acts perpendicular to the beam, so this force is at 90 degrees from point A. So the line of action is at the distance of 6.0 meters perpendicular. A vertical force Y and a horizontal force X both act at end B of the beam. State the name of force X. Of course, force X, because it is between the beam and the surface, that's most like a frictional force. That's most likely a frictional force. By taking moments about end B, calculate the weight W of the beam. So X and Y will have no moment. W is causing anti-clockwise. Then this one is causing clockwise. So we are taking moments about B. So we shall have W times its perpendicular distance. Let's find the perpendicular distance. So this is the perpendicular distance. This distance here is 3 meters because W is the weight of the beam. So the distance to the center is 3 meters. So we want the adjacent. We have the hypotenuse, that is cos. Cos of 31 is equal to the adjacent over the hypotenuse. So that is 3 cos 31. So this is going to be 3 times cos 31. That is the distance. That is anti-clockwise moment should be equal to the clockwise moment. Since they gave us the perpendicular distance of the 90 newtons from A, so here we just say 90 times 6. So we check 90 times 6 divide by 3 cos 31. So that is 209.99. So W is 209.99. Approximately it is 210 newtons. Then determine the magnitude of force X. Force X is in the horizontal. By all means, I need to find, since the beam is in equilibrium, I must find 90 newtons in the horizon. So let me draw a horizontal line here so that I resolve 90 newtons in the horizon. So I have to find 90 newtons in the horizontal. You and me will see that this angle here is also 31. It is the same as this one here. So this angle is 31 degrees, meaning because the beam 90 newtons was at right angles, so this angle is going to be 90 minus 31, which is 59 degrees. So when I resolve 90 to the horizontal, it will be 90 cos 59, or it will be 90 sine of 31. So that force must be equal to X because there should be no reason. It is the only force or component in the horizontal. So I will say to determine X, X is going to be equal to 90 cos 59 or 90 sine 31. The cos of 59 is the same as the sine of 31. So 90 cos 59, that is 46.3 or approximately 46 newtons. A wire hangs between two fixed points as shown. A child's swing is made by connecting a car tire to the wire using a rope and a hook. The system is in equilibrium with the wire hanging at 17 degrees to the horizontal. The tension in the wire is 150 newtons. Assuming that the rope and the hook have negligible weight, determine the weight of the tire. So the weight of the tire is vertically downwards, W. So we are going to resolve the tensions in the vertical, and they are identical, so we should just multiply that by 2 or sum them up. So if I resolve, maybe I can put a horizontal line here so that people see that the angle down there is also 17. So this angle is 17 degrees, this is also 17 degrees. So when I resolve using 17 degrees to the vertical, it will be 150 sine of 17, but there are two. Even for the other one, it will also be 150 sine of 17. For equilibrium, those two should be equal to the weight downwards. So the weight W is equal to 150 sine 17 plus, again, 150 sine 17. So just say 150 sine 17, and I multiply it by 2. So that is 87.7. Sorry, 87.7, or approximately 88 newtons. The wire has a cross-sectional area of 7.5 millimeters squared and is made of a metal of Young modulus 2.1 times 10 power 11 pascals. The wire obeys Hooke's law. Calculate for the wire the stress. So we know that stress is equal to force over area. The tension is 115, then the area is 7.5. Because it's millimeters squared, it is millimeters times millimeters. So that will be 7.5. To change from millimeters to meters, that will be times 10 power negative 3, again times 10 power negative 3. So this will be 7.5 times 10 power negative 6. 150 divided by, open brackets, 7.5 exponent negative 6. That is 20,000. Yeah, 20,000 or 2.0. No, 20 millions. 2.0 times 10 power 7. That is 20 million. Okay. Then the strain. Since we don't have extension, we don't have original length, we can use stress Young modulus as being stress over strain. So Young modulus is equal to stress over the strain, which means the strain is equal to the stress divided by Young modulus. So we shall find the stress is 2.0 times 10 power 7 divided by Young modulus has been given as 2.1 exponent 11. So that is 2.1 times 10 power 11. So divide by 2.1 exponent 11. So that is 9.5 times 10 power negative 5. Okay. A cylinder is suspended from the end of a string. The cylinder is stationary in the water with the axis of the cylinder vertical as shown in the diagram. So the cylinder has weight 0.84. The weight is acting vertically downwards. Of course, there is an upthrust force U. There is tension, that is T. The density of the water is 1000. The difference between the pressures on top and bottom of the face of the cylinder is 520. Calculate the height h of the cylinder. So this is easy. If the difference in the pressure is equal to 520, remember difference in the pressure is density times g times difference in height h. So 520 is equal to 1 times 10 power 3 times density, g, which is 9.81 times the height h. So we have 520 divided by, open brackets, 1000 times 9.81. That is 0.053. 0.053. Show that the upthrust acting on the cylinder is 0.39. Remember, upthrust is due to the difference in the pressures on top and bottom, which cause a difference in force on the top and the bottom. And the force at the bottom is greater than the force at the top because pressure increases with the depth. So the upthrust is equal to the cross-sectional area times difference in pressure. And of course, the area is going to be pi r squared, which is going to be pi d squared over 4. Okay, so let's substitute. So the upthrust is going to be the cross-sectional area. I will begin with the pressure, change in the pressure, which is 520. Then the area will be pi over 4 times d squared, which is 0.031 squared. 0.031 squared. So I'll press my calculator. 520 times pi. Maybe divide by 4 times 0.031 squared. That is 0.39. Then calculate the tension T in the string. I think they talked about is it in equilibrium? The cylinder is stationary in water, so that means it is in equilibrium. So the forces acting upwards were the tension in the wire plus the upthrust, which is equal to the weight for equilibrium. So the tension is going to be the weight of the cylinder. What is the weight? The weight is 0.84. 0.84 minus the upthrust, which is 0.39. And that gives us 0.84 minus 0.39, which gives us 0.45. Okay. The string is now used to move the cylinder in air vertically upwards through the water. The variation with time t of the velocity v of the cylinder is shown here. So let's see here, it's 2.5. Determine the acceleration of the cylinder at t equals to 2.0. So 2.0 is here. Of course, this is a straight line, so I just find the gradient. Can just find the gradient or change in velocity over time. So acceleration can be v minus u over t, or that can be change in velocity over time, or you can just say it is equal to the gradient. So the acceleration is going to be, I think this is 8, because the scale on the vertical is 2.5 divided by 5. 2.5 divided by 5, that is 0.5. Each small square is 0.5. So you have one small square here, which makes it 8. So that is 8.0, but it is in centimeters per second. So it will be times 10 power negative 2 minus 0 divided by, the time is 2 minus 0, which is 8 divided by 2, that is 4, times 10 power negative 4.0 times 10 power negative 2. The top face of the cylinder is at a depth of 0.32 meters below the surface of the water at time t equals to 0. Use the figure to determine the depth of the top face below the surface of the water at time t equals 4 seconds. Let's see what distance will the cylinder have moved, which is going to be the area under that graph. So the distance is equal to the area under the graph. And that distance is equal to, the area under the graph is a half times the base, which is 0.4, Is it 0.4? Yes. It is a triangle, the base is 0.4 and the height is, I think the height is 10.0 centimeters per second. So the height is 10 times 10 power negative 2 to change it to meters per second. So we press our calculator to find that area. 0.5 times 0.4 times 10 exponent negative 2. So that distance is 0.02 meters. So the distance covered in 4 seconds is 0.02. I mean 0.2. It is 0.2. Let me check again. 0. Oh, by the way, the base is 4, not 0.4. This base is 4, not 0.4, because we are finding the area under the graph. The base is 4 seconds, so this is 4. So this means this is 0.2. Sorry for that. So the distance moved in 4 seconds is 0.4, 0.2, but the top face of the cylinder is at a depth of 0.2 meters below the surface of the water at time t equals to 0. But after 4 seconds, it has moved a distance of 0.2 meters. Note that the cylinder is moving. Where is the cylinder moving? Okay. The string is now used to move the cylinder vertically upwards. So the cylinder is moving vertically upwards. It means the distance is reducing from 0.32. So we subtract. So this means the depth is 0.32 minus 0.2, which is going to be equal to 0.12. The cylinder in B is released from the string at time t equals to 4 seconds. The cylinder falls from rest vertically downwards through the water. It is falling vertically downwards through the water, assuming that the upthrust acting on the cylinder remains constant as it falls. State the name of the force that acts on the cylinder when it is moving and does not act on the cylinder when it is stationary. Of course, that is friction, which is viscous force. State and explain the variation, if any, of the acceleration of the cylinder as it falls downwards through the water. So as it is falling downwards through the water, the weight is downwards, the upthrust is upwards and is constant. Viscous force is going to be upwards, that is the viscous drag. As it is falling downwards, the viscous drag is increasing upwards. Remember the acceleration, the resultant force is going to be the weight minus upthrust plus the viscous drag. As it is falling downwards, the drag is increasing. It means the difference here is going to be smaller. So the resultant force is decreasing. Therefore, the acceleration is decreasing. So the viscous force increases with the speed or with the depth. Viscous force increases with the speed or with the depth, because as depth increases, the speed is increasing. So the resultant force decreases. So hence acceleration decreases. Acceleration decreases. Okay. A solid cylinder of weight 24 newtons is made of a material density 850 kilograms per meters cube. The cylinder has a length 0.18 meters as shown in the figure here. Show that the cross-sectional area of the cylinder is 0.016 meters squared. So they have given us the mass, the density, and they have given us the weight. So to start with the weight is equal to mass times G. Mass is equal to density times volume, then we multiply this by G. And volume is equal to cross-sectional area times H. Then we shall multiply this by G. So I'll say the weight is 224 is equal to the density, which is 850, times G, which is 9.81, times H, which is 0.18, then times A. I'll just press the calculator to get a 24 divided by 24 open brackets 850 times 9.81 times 0.18. All of them were in SI units, so that one I just press the calculator, and this is 0.01599, which is approximately 0.016. So that is A. The cylinder is attached by a spring to the bottom of a rigid container of liquid as shown here. So we can think of the forces acting. Number one, there is a weight, weight is vertically downwards. Number two, there must be an upward force, which is the upthrust. And if the cylinder is pushed upwards, then it means there is tension in the spring, which is going to be downwards. There is tension downwards. The cylinder is in equilibrium. That is enough to tell us that the upward force is equal to the total downward forces. So upwards we have the upthrust. Downwards we have the tension plus the weight. So the upthrust is going to be the tension, which is 8 newtons, plus the weight, which is, I think the weight is 30, is it 32? Show that the upthrust acting on the cylinder due to the liquid is 32. So the tension is 8, and the weight, the cylinder in A. So let's check in A, the weight of cylinder in A, it was 24. So the cylinder in A, the weight is 24. So this is going to be 32. Note carefully how we arrived at this. If it is immersed in a liquid, there is an upward force. Its weight is always acting downwards. Then the force in the spring must be towards the spring. So it is downwards. Then calculate the density of the liquid. So since we have the upthrust, and we now know that the upthrust force is cross-sectional area times the difference in pressure on the top and the bottom of the object. So, and by that we also know that the difference in the pressure is equal to the density times G times the difference in height h. So we now substitute, or we make, because I want density, I'll make the density the subject. The upthrust is 32 equals to the cross-sectional area. The cross-sectional area of the cube, I think it was, of the cylinder was given. The area was 0.016. So this is 0.016 times density. The density is what we want to find, times G, which is 9.81, times H. Of course, the difference in the value of H will just be equal to the height of the cylinder, which has been submerged, and that is 0.17. So this will be times 0.17. So we find the density by dividing. So that will be 32 divided by, open brackets, 0.016 times 9.81 times 0.17. So that is 1199. 1199. kilograms per meters cubed. This is 1,200. The figure shows the variation of the tension F with the length of the spring in B. The tap at the bottom of the cylinder is opened so that a fixed amount of liquid flows out of the container. The cylinder moves downward so that the tension in the spring changes from 8 newtons to 4 newtons. From 8 newtons to 4 newtons, 8 newtons to 4 newtons. 8 newtons to 4 newtons. Okay. Determine the change in the elastic potential energy of the spring. So the tension changes from 8 newtons to 4 newtons. So 4 newtons is here, 8 newtons, that will be the area under that part. Area under that part. So the elastic potential energy will be given by the area, or the change in elastic potential energy could be given by the area under the graph. Or it would be given as a half F times X. So we would get a difference. The difference in energy would be, the area under that graph would be a half times what would be like a B, or what would be like A is 4, I guess, plus what would be like B is 8, I guess. What would be like H is from 70 to 20, I mean to 50. 70 minus 50. 70 minus 50, but this is times 10 power negative 2, which is I think 20. So let's check. This is 0.5 times 4 plus 8 is 12, times 70 minus 50 is 20, exponent negative 2. So that is 1.2. So this is 1.2 joules. Alternatively, we could use the formula half Fx. So the difference in energy would be initially from 80 newtons, this would be a half times 8 times times the extension, that is now from 30 to 70, because the original length is 30. So x is 70 minus 30. That is 70 minus 30 times 10 power negative 2 to change it to meters. That is energy for force equals to 80 minus for force equals to 4. The other 8, force was 8. Force equals to 4 is a half times 4 times, now at 4, that is 50 minus 30. 50 minus 30 times 10 power negative 2. So we can find a difference, open brackets, 0.5, that is a half times 8 times 30 minus 40, 70 minus 30, that is 40. 40 exponent negative 2. Then minus, again the other one is a half, 0.5 times 4 times 50 minus 30, that is 20, exponent negative 2. And that is still 1.2. So the difference in energy is still 1.2 joules. More liquid is let out of the container until the upthrust on the cylinder becomes 24. For the upthrust of 24, determine the length of the cylinder. Determine the length of the cylinder. So when the upthrust equals 24, remember the weight was 24. When the upthrust equals to 24, remember the weight was 24. Determine the length of the spring. So it means upthrust, which is upwards, plus the tension in the string is equal to the weight. But remember the upthrust is equal to the weight. So that means the tension in the string is the weight minus the upthrust. So the tension in the string is equal to 0 because the weight is 24 and the upthrust is The weight is 24 and upthrust is 24. The tension is equal to K times the extension. The extension is going to be 0. So it means the length is 0. No, the length is not 0. The extension is 0, the length is 30. The extension is 0, so the length is remember length is equal to the original length plus the extension, which is equal to 30 plus 0. So the length is now still 30. So the spring goes back to its original length, 30. I'm saying the tension is weight minus upthrust, but the weight was 24. Now if the upthrust is also 24, it means the tension is 0. That means the extension of the spring is 0. So the length of the spring will be the same as its original length, which is 30 centimeters. A sphere of radius 2.1 falls with a terminal constant velocity through a liquid. Let's first draw arrows for the forces acting. Maybe it is a question there. 3 forces act on the moving sphere. The weight is that. The upthrust is that. The viscous force Fv is that. So the weight acts vertically downwards, that is the weight. Then the upthrust acts vertically upwards, that is the upthrust. I will call it U. The viscous force acts to oppose its motion, that is Fv, upwards. Determine the SI base units of K. So we begin by making K the subject. K is equal to Fv divided by Rv. So Fv is a force, which is kilogram meters per second squared. So that means, and of course V is speed, meters per second. R is radius, which is meters. So the units of K will be kilogram meters per second squared divided by meters times meters per second. 1 m has cancelled, so you remain with kilogram meters power -1, s power -2, and s power -1. I think that is s power -1. So you get kilogram per meter per second. Use the value of the upthrust acting on the sphere to calculate the density rho of the liquid. We want to use the value of the upthrust to find the density rho. So upthrust is equal to cross-sectional area times difference in pressure, which is actually equal to the weight of the liquid displaced. So upthrust is equal to the weight of displaced liquid. So the upthrust is equal to the displaced liquid. So this is going to be equal to mg, which is going to be equal to m is density times volume, then times g. And remember the volume of a sphere, because it is a sphere, volume is 4/3 pi r cubed. So it means we shall simply say that the upthrust, which is given as, what is the upthrust? The upthrust is 4.8. The upthrust is 4.8, so we shall say that 4.8 times 10 power -4 is equal to the density, which density we want to find, times g, which is 9.81, times the volume, which volume is 4/3 pi, times the radius of the sphere. The radius of the sphere is 2.1 millimeters. So I will say 2.1 times 10 power -3, and that is raised to power 3. So we can check. So since I want the density, I will just make the density the subject. but I know some of us are not good at math. But I'm dividing both sides by this quantity here. So I'll simply say 4.8 exponent negative 4. I'll multiply by 3, cross multiplying. Then divide by, open brackets, 9.81 times 4 pi. Then times, I open another bracket, 2.1 exponent negative 3 raised to power 3. I close that bracket. So that gives me 1261. So the density is 1261 kilograms per meters cubed, or approximately 1300. You can first calculate step by step. You calculate the volume, you calculate, then you substitute, you find the mass, but you'll not be able to find the mass because you need the density and you want to find the density. On the sphere in the figure, draw 3 arrows to show the direction of the weight, the upthrust, and the viscous force. I think we have drawn this one there. We have labeled them. Weight downwards, upthrust upwards, viscous force upwards. Then determine the magnitude of the terminal velocity of the sphere. So for a terminal velocity, the resultant force is 0. That means the weight downwards should be equal to the upthrust plus the viscous force upwards. And since we want to find the terminal velocity of the sphere, we need to substitute an expression for the viscous force. So the viscous force Fv is going to be equal to the weight minus the upthrust, but the viscous force was given by an expression that we saw up here, KRV. So that is KRV. KRV is equal to the weight, which is 7.2 times 10 power negative 4 minus the upthrust, which is 4.8 times 10 power negative 4. Did they give us K? K is a constant. K is, the value of K in SI units is 17. R was the radius, and I think they gave us the radius as 2.1. So we just substitute. K is 17. The radius is 2.1 times 10 power negative 3, then times V is equal to that difference. I think that is 7.2 minus 4.8. 7.2 minus 4.8, I think that is 2.4. So that is 2.4 times 10 power 4. So we have 2.4 exponent negative 4, not power 4. That is exponent negative 4. Divide by, open brackets, exponent 4. Divide by 17 times 2.1 exponent negative 3. So that is 6.7 times 10 power, is it positive 3? Let's check again. 2.4 exponent negative 4. Yeah, divide by 17 times 2.1 exponent negative 3. Okay, so that was a typing error. So that is 1236.7 times 10 power negative 3. 6.7 times 10 power negative 3. State what is meant by center of gravity. So center of gravity, at this point we now know center of gravity is the point where all the weight all the weight of the object may be considered to act. That is center of gravity. So the point where all the weight of the object seems or is taken to do what? It is taken to act, it seems to act, that is center of gravity. A non-uniform rod, it is non-uniform, is pivoted at point P as shown in the figure. The rod has length 4 meters and weight 44 newtons. The center of gravity of the rod is 1.7 meters from the end X of the point of the rod. Point P is 1.1 meter from end X. A sphere hangs by a wire from end Y of the rod. The weight of the sphere is 3 newtons. The weight of the wire is negligible. A force F is applied vertically downwards at end X so that the horizontal rod is in equilibrium. By taking moments about P, calculate F. So F is causing anti-clockwise, 44 will be clockwise, 3 newtons will be clockwise, about point P. So by taking moments about P, we have F times its perpendicular distance, which is 1.1, should be equal to 44.0 times the perpendicular distance. Perpendicular distance of 44.0 is this one here, which is 1.7 minus 1.1, which is 0.6 meters. So this will be times 0.6. That is 1 plus another clockwise moment is 3.0 times its perpendicular distance. The perpendicular distance of 3.0 from the pivot is this distance here, which is 4 minus 1.1. It is 4 minus 1.1, which is 2.9. So that is 4 minus 1.1, which is 2.9. This is 2.9 meters. So when we press our calculator, so 44 times 0.6 plus 3 times 2.9, then we divide this by 1.1. So that is 31.9. 31.90 is repeating itself, 9090 and so on and so forth, which is actually 32. Calculate the force exerted on the rod by the pivot. So for equilibrium, the resultant force must be 0. All the forces downwards should sum up with the forces upwards. So the force at P is going to be the sum of the forces downwards. So the force at the pivot, F at P, is going to be equal to the forces downwards, that is F, which is 32, plus the weight of the beam, which is 44, plus the weight of the sphere, which is 3.0. Total forces upwards should be equal to total forces downwards. So 32 plus 44 plus 3, which is 79. So this is 79 newtons. The sphere in B is now immersed in a liquid. What is the effect of immersing the sphere in a liquid? There is an upthrust force. It means the force here, the weight downwards, or the force causing moment here is going to be reduced. It appears to be less, it appears to be weightless. So there is a tension there. There is an upthrust force. Okay, the density of the liquid is 1100. The upthrust acting on the sphere due to the liquid is 2.5. So upthrust, the upward force is 2.5. This is 2.5 newtons. The magnitude of F is unchanged. What was the weight? The weight was 3. So the weight is 3, but the upthrust is 2.5. 3.0. That means not all the 3.0 is causing a clockwise moment. It is now a difference. The force causing a clockwise moment is going to be the difference, which is 3.0. But if it is in equilibrium, then the tension upwards plus the upthrust should be equal to the weight. So the tension would be 0.5. Let's see. The magnitude of F is unchanged so that the horizontal beam is not in equilibrium. Use Archimedes' principle to determine the radius r of the sphere. Archimedes' principle states that the upthrust on an object immersed in a fluid is equal to the difference, or is equal to the weight of the liquid displaced. That is, I'll write it here. Archimedes' principle states that upthrust is equal to the weight of the liquid displaced. That is Archimedes' principle. So the upthrust force F is equal to the weight mg, which weight m is density times volume, then times g. So the upthrust is 2.5. So the upthrust is 2.5. The density is 1100 times the volume, which we don't know, then times g, which is 9.81. So remember, we want to determine the radius of the sphere. So using the upthrust, we are able to find the volume. But note that the volume of a sphere is 4 over 3 pi r cubed. So it means the volume, which is 2.5 divided by 1100 times 9.81 should be equal to 4 over 3 pi r cubed. So I'm just going to press my calculator to get the radius. So 1, I will divide 2.5 divided by, open brackets, 1100 times 9.81. So that's what I get, times 3 divided by 4 pi. I'm making r cubed the subject. So divided by 4 pi. Then I find the cube root. Shift cube root of the answer. And that is 0.038. So r is 0.038. So I used the upthrust to find the volume, and I equated the volume to the formula for volume of a sphere. As simple as that. Calculate the magnitude and direction of the resultant moment of the forces on the rod about P. So first of all, there is a resultant moment. So the resultant moment is just due to the upthrust. The resultant moment is just due to the upthrust because the only new force here is the upthrust. So you could simply look at it as the resultant moment. The resultant moment is just due to the upthrust, which will be the upthrust force times the distance, and this would be the upthrust is 2.5 times the perpendicular distance of the upthrust is 2.5, the perpendicular distance from where we took moments, I think it was 2.9. It was 2.9. And this gives us 2.5 times 2.9. So that is 7.25. 7.25, and this will be the direction of this moment, that is going to be anti-clockwise. Because the upthrust is upwards, this is going to be anti-clockwise. Alternatively, you can look for the resultant force when the mass is immersed in the liquid, when the sphere is immersed in the liquid. And the resultant force, the direction of the resultant force is the one which is going to cause, the direction of the resultant force is the one which is going to cause an extra moment. When you look at the spring, you notice that the upthrust is 2.5 upwards, the weight is 3.0 downwards. Therefore, it is the tension in the string which is going to be 3.0 minus 2.5, that is 0.5, which is going to now cause a moment. So that means the force F times its perpendicular distance 1.1. I have to subtract the moment because that one is causing F is still causing anti-clockwise moments, but 44 is causing clockwise moment, and there is a resultant force of the here which is acting downwards. There is a resultant force here which is going to be causing another moment. So that means we shall subtract that. So this will be minus 44 times 0.6 plus the difference in the forces 0.5 times the perpendicular distance, which is 2.9. So you can think about the extra force here, which is going to be the tension acting upwards. And by the way, this is not causing clockwise, it is causing actually anti-clockwise. The tension here is going to be causing an anti-clockwise moment about the beam when the sphere is immersed. So we have this one here, minus 44 minus, where are we taking moments? Calculate the magnitude and direction of the resultant moment of the forces on the rod about P. The density of the liquid is that, the upthrust acting on the sphere due to the liquid is that, the magnitude of F is unchanged so that the horizontal rod is not in equilibrium. The sphere in B is now immersed in a liquid in a container. Okay, so we just consider the upthrust as being responsible for the resultant moment because the upthrust reduced the effect of the weight. So it made the anti-clockwise moment, it made the clockwise moment to be smaller. Therefore, the resultant moment should be the other way around to balance to balance with the clockwise moments which have been reduced. So the moment is going to be 7.25 times 7.25 and it is anti-clockwise to balance the moment due to the upthrust, balance the moment due to the reduction in the weight of the object, or due to the apparent weight of the object. Okay, I think I'm tired. Let's end with this question. A sphere is attached by a metal wire to the horizontal surface at the bottom of a river as shown. So let's show the forces first. Weight is vertically downwards. Because the water is pulling away, the tension is going to be downwards. So this is acting horizontally. And if I draw a horizontal line here, you notice that this angle will also be 68 degrees. Of course, upthrust acts vertically upwards. The sphere is fully submerged and in equilibrium with the wire at an angle of 68 degrees to the horizontal. The weight of the sphere is 32 newtons. The upthrust acting on the sphere is 280 newtons. So there is an upward force acting on the sphere that is 280 newtons, that is upthrust. The density is 1000 kilograms per meters cubed. Assume that the force on the sphere due to water flow in the horizontal direction assume that the force on the sphere due to the water is in a horizontal direction. By considering the components of force in the vertical direction. Components of force in the vertical direction determine the tension in the wire. Determine the tension in the wire. The sphere is fully submerged and in equilibrium. So, which forces are acting? Here we have the upthrust, we have the weight and the tension in the wire, which can be resolved vertically downwards. Resolving T in the vertical, if this angle is 68, T in the vertical downwards will be T sine 68. So resolving T in the vertical, we have that T sine 68. It will add to the weight to balance with the upthrust for equilibrium. So it means T is going to be equal to 280 minus the weight, which is 32, divided by sine of 68. 280 minus 32 divided by sine of 68. So that is 267. T is 267, which is 270. For the sphere, calculate the volume. Of course, volume of the sphere is the same as the volume of the liquid displaced. So volume of the sphere is going to be the same as the volume of liquid displaced. So we can find this from the upthrust. We know that the upthrust is equal to the weight of the liquid displaced, which is equal to mg, which is the same as m is density of the liquid times volume of the liquid times g. The upthrust was given as 280. Remember, upthrust is equal to the weight of the liquid displaced. Upthrust is the weight of the liquid displaced. So 280 is going to be the density, which is 1.0 times 10 power 3, then times the volume of V times 9.81. So let's find 280 divided by 1 exponent. Let me start with 9.81. 9.81 times 1 exponent 3. So that is 0.029. V is 0.0285 or 0.029. Okay. Then the density so since we have the volume, we want density as mass over volume. So density is mass divided by volume. But we have the weight, we don't have the mass, I think. The weight is 32 newtons. So mass is weight. Mass is going to be the weight divided by g. So the density will be equal to the mass, which is weight 32 divided by 9.81. Then we divide this by the volume, which is 0.029. So we have 32 divided by 9.81. Divide the answer by 0.029. So that is 112. So this is 112 or approximately 110 kilograms per meters cubed. The center of the sphere is initially at a height of 6.2 meters above the horizontal surface. The speed of the water then increases, causing the sphere to move to a different position. This movement of the sphere causes its gravitational potential energy to decrease by 77 joules. Calculate the final height h. the final height of the center of the sphere above the horizontal surface. So we can find from the difference in gravitational potential energy as mg times the difference in height h. Remember, mg is the weight times the difference in height h. So the difference in height h is going to be the potential energy, which is, it is actually decreased. So I can say, okay, that is potential energy is 77 divided by the weight, which is 32. So this is going to be equal to 77 divided by 32. That is 2.4. So this is 2.4 meters. That is the difference in height. But remember, this potential energy was a decrease in potential energy. So that means the height was decreasing. So the final height will be the difference. The final height is going to be 6.2 minus 2.4 because there was a decrease in potential energy, so the height was decreasing. So this would be 3.8. If the height was increasing, we would simply add. Okay. Is it 6.2 minus 2.4? Yes, 3.8. Extension of the wire when the sphere changes position as described in C. Extension of the wire increases when the sphere changes position as described in C. The wire obeys Hooke's law. State a symbol equation that gives the relation between the tension T in the wire and its extension X. Identify any other symbol that you use. Of course, we know tension is equal to K times X, where K is a constant. Where K is a constant of the wire. Of the material of the wire. That is the spring. If it was a spring, it would be a spring constant. Somebody will talk about T to be equal to, instead, that would be EA over L times X, where E is Young modulus. That is, if you use the formula, E is equal to T over area times extension over original length. So it means T is equal to EA. T would be equal to E. No, this would be original length. It is L because it is strain. So this will be original length over extension X. So that makes T to be equal to E times A over L times X, where E is Young modulus, A is cross-sectional area, and L is original length. Okay, so last but not least, of course, our next unit might be kinematics. So we have kinematics and electricity to finalize with AS 2. Then we shall embark on paper 1. Before the sphere changed position, the initial elastic potential energy of the wire was 0.65 joules. Before the sphere changed position, the initial elastic potential energy of the wire was 0.65 joules. The change in position of the sphere causes the extension of the wire to double. Calculate the final elastic potential energy. So let's use mathematics. Initial kinetic elastic potential energy E1 is equal to a half kx squared. And this is going to be 0.65 equaling to a half times k times x squared. Let x be the initial extension. Then E2 is going to be equal to the change in position of the sphere causes the extension of the wire to double. So E2 is going to be a half k. Where there is extension, I'll put there twice x, but this is squared. That means E2 is equal to a half k times 4x squared. So this is going to be the same as a half k x squared, but this is times 4. That is times 4. But a half kx squared is 0.65. So this is 0.65 times 4. So it means the new energy is going to be 0.65 times 4, which is a 2.6. This is 2.6. So the final energy is 2.6. If that is very hard, you can first find the extension x. So method 2. Method 2, we can use elastic potential energy is equal to a half times F times X. So 0.65 equals to a half times F. What was the initial value of F? I think the tension was, what was the tension? We calculated the tension. The tension is 270. I will use 270 or 267. So this will be 270. So this will be times 270, then times x. So I can find x here, initial value of x. X is going to be 2 times 0.65 divided by 270. So x is 4.8 times 10 power negative 3. Then the change in position of the sphere causes the extension of the wire to double. So this x can also help us find the constant, because the constant will remain the same. So the constant k is going to be equal to F over x. F is 270 divided by x, which is 4.8 times 10 power negative 3. So 270 divided by the answer. So this is 5.6 times 10 power 4 newtons per meter. That is the constant. So now let me find a new value of E2, which will be a half times, I will use a half because I don't know the second force. I will use this is the extension. The spring constant is that. So I think I should use a half kx squared. So this is going to be a half kx squared. I'll use kx squared. So this is going to be a half times k, which is 5.6 times 10 power 4, then times x. Now remember x doubles, so this will be 4.8 times 10 power negative 3, then this is times 2, but this is squared. Let's check this. So a half is 0.5 times 5.6 exponent 4, then times, I will open the brackets, 2 times 4.8 exponent negative 3, but this is squared. So that is 2.58. So this is 2.58, which is approximately 2.6. So this method too could also be fine, but will require a lot of patience. Okay, so that is finally the end of force, density, and pressure. Sorry if I made some mistakes. I am bound to make errors because sometimes I record the videos with a lot of flu. I have sinuses, so I record the videos with a handkerchief in my hand. So the thinking capabilities can be affected by the condition I'm in, and sometimes I will make some errors. But nevertheless, I try my level best to make the videos understandable I try to give alternative methods. I try to do the algebra for some PCB students, and I hope at least you learn a few things from these videos. Nevertheless, I wish you the best, and let's meet in kinematics. Bye bye.